Good morning, sir. Puneet, sir. Good morning.
Good morning.
So what do you suggest? Should we start with the session? Like 142 participants joined.
Yeah, we can start with basically if there are any questions, we can start with questions right away, and then in another 5 minutes we'll start.
Okay, sure, sir. So good morning, all the participants. We request you to please, if for the previous session you have any question, I request you to please put it in the question answer section. In the meantime, all the other participants will be joining, so we will start the session. Thank you.
Okay, looks like not many questions. Seems like most of the people haven't even joined yet. So what we'll do is we'll do a quick recap of what we learned yesterday. So that I'll try to do it very quickly, and then we'll go into today's session. Okay, so yesterday we learned the OOP principles. All right, so we learned, I'll start from here very, very quickly. So we learned that there are two kinds of design flow methodology. One is waterfall and the other is agile. And in agile, you want to have reuse, you don't want any rigidity. That means basically if if there is a change in the specification, we are able to implement it quickly. And all this is possible only if we have minimal binding between different parts or different components of our software system. And all this we are learning because we want to learn how verification, which is an object, basically the UVM verification, which is an object-oriented platform, how it is structured. And we want to avoid rigidity, fragility, immobility, and viscosity. So those were the bad smells of software. And then we learned how the verification libraries or verification test bench is structured. We have base class library, which is the top level abstraction, and then we had verification IPs as well as the top level integration environment of whatever test bench you are creating, and finally the lowest level abstraction is the test cases. Then the important parts of what we learned in object-oriented programming is basically we learned the principles. We learned single responsibility principle, and this is that each class should have only one reason for change. All the basically the constituents of the class or whatever code we put in the class, it should be aligned to one concept. Because if we start mixing up classes and if we make bigger classes having too much stuff in it, then obviously there's tight binding. For example, if we just create one class for the whole project, then it's like having global variables because all the functions in the class will be sharing the variables, and that will lead to a lot of rigidity and fragility. So we want to have small classes which are which just have one concept. And then we went into open close principle, which is instead of allowing people to modify a class, we should allow them to extend it. And yesterday I missed a little part of it. So basically it becomes more important in verification because in many cases we get PIPs, for example, which are encrypted. So even if we want to modify them, we can't because the code is encrypted. And though UVM, even with system Verilog, UVM is not encrypted, though it is open source. The VIPs, if we buy from various vendors, will be encrypted. So there is no scope for modification. But if we are using system Verilog and UVM, for example, then the UVM library is structured in such a way that it allows us to add functionality to those classes by way of extending the functionality through inheritance. Otherwise, from object-oriented principles, we would like to have class, inheritance becomes important because if we start modifying base class for extending it, then there are people who are using the base class for, a generic purpose. For example, the base class could be shape, and then you extend it and create a square and a rectangle and a triangle and so on. So if we start putting code of a square into the base class, then people who are using a circle will start getting affected, and that will result in tight binding. So we want to have a base class, and then we want to have extended classes. So another point here is that when you have a base class, or any class for that matter, there can be two types of clients of that class. One is people who instantiate that class to create objects, and they have an interface to it, which is the public interface. And similarly, there are other kinds of clients, people who extend that class to create other classes. So they are also clients to the base class, and they see the public interface, as well as they see the protected methods of the class, and those methods are visible only to this kind of client who is extending the functionality. So every class will have, for that matter, multiple clients. One is clients who see public interfaces, and there could be multiple public interfaces, and then the clients who see the protected interfaces, and those will be the ones who inherit from it. Okay, so going forward, we looked at how cryptid frame, which would inherit from, a generic Ethernet frame, would do it by having some, by creating, by using inheritance, and then by, um, by overriding the virtual, or the virtual functions, and by having some private data in the extended class, which is useful for the override, the functions you have overridden, and therefore some data, or some memory basically would be required to, basically I want to say the state of the program, which is into state variables. So those variables will be required for the overridden function, and that's why the extended class could have its own private area. So the difference between private, public, and private and protected, we discussed that yesterday. And then we discussed is a relation versus has a relation, and we discussed how having inheritance helps you uh, with reversing dependency. So that was so we had Liskov substitution principle, and then we had dependency inversion. And this is where, the whole concept of UVM becomes clear, because UVM is the top level abstraction. And so therefore, UVM provides us with the top level algorithms of verification, and then we fill in the lower level details to have the verification flow ready. So normally when you use a library in non-object oriented platform, it's a normal library like C libraries, then there is a dependency of the library which is low level, which is for example, you have printf function, it's a low level function, or you have math libraries, all the low level algorithms of mathematics. So when you use a library, then you are working at the higher abstraction level, and you use the library from the lower abstraction level with UVM kind of platforms, and those are called base class libraries. So UVM is a base class library. The dependency is inverse. The top level algorithms are defined, and that's why it's a methodology, because it has top level algorithms, and those algorithms do not have dependency on the lower level details. Otherwise, people wouldn't be able to write a top level methodology when they don't know what the lower level details are. So they are able to write it independently because of this dependency inversion principle. And then you fill in the lower level details, and you are able to create the flow. So UVM will not tell you whether you are verifying a processor or you are doing a network. You are doing a network chip and therefore verification of the network chip. But when you fill in those details, UVM will assist you with the top level verification. Al I won't say algorithms, but top level verification flow, and that flow will be available for you to do your test bench. Okay. So this is what we discussed, and then we had interface segregation principle, and yeah, that was it. Now we will go into design patterns today, and we will learn how different types of design patterns are implemented in UVM. So typically we will learn the UVM phases, and we will also learn, more importantly, the factory pattern. So there are two factory patterns, the abstract factory pattern and the discrete factory pattern. We'll learn both of them. But before we start all that, since yesterday we were running late, so we didn't discuss we weren't able to discuss the SHA3 test bench. So that's what I'll be doing now. All right. So on to SHA3. Okay, a little bit of introduction to SHA3. SHA3 is the most modern encryption algorithm. So with SHA2, which is in use today. So whenever you do HTTPS, or whenever you are logging in into a remote server, you are using SHA2. But with time and with advances in computability, SHA2 will be slightly shaky. Like there were instances where people were able to break encryption, though it took them 6 months to do that. But so you get the idea, like you need a new standard in for future where you need stronger encryption. Now, there is more to SHA3. When they started with the new standard, with defining the process of defining the new standard, one of the goals of the new standard was efficient hardware implementation. So you see my point. Software, because of what we discussed on the first day, because of in 2005, as we discussed, the software hitting uh, basically the clock frequency of computers, of the processors, has started getting stagnated. It's stuck at 3.5 gigahertz to 4 gigahertz. So software cannot become faster, and therefore people are going to use more hardware. And when they started defining this SHA3 algorithm, they had a competition and various teams. I think there were about 20 teams who participated. So the point was to have a standard which also can have a very efficient hardware implementation. Okay, efficient would mean it is quick, as well as it doesn't take too much area on silicon or on the FPGA. So what I see in future is, as we move from SHA2 to SHA3, such algorithms will need to be on hardware, because it's like you have a processor, and even today processor is doing a lot of things in hardware. For example, you have DMA, and when the processor wants to move some memory block from one memory block to another memory block. These could be, for example, transfer from Ethernet buffer to the main memory. So if the processor starts doing it itself, then the processor will be taking too much time reading each location from Ethernet buffer and then copying that into the memory. So it doesn't happen this way. Processor instead will use DMA, and DMA, it will give the instruction to DMA, okay, from this address to this address, it wants data to be copied to another memory block. Okay, the same way in future, you'll have algorithms, and for those algorithms, the processor will, instead of doing those algorithms itself, the processor will delegate that algorithm to specific hardware. It may be uh, maybe ASIC, like, for example, DMA is part of the processor. So in future, for example, some processors will have SHA3 as part of the processor. So that will be a block on silicon, or it may be FPGA. So in some cases, it will be FPGA. So the processor will say, okay, I want SHA3 right now, so let me load it into the into the FPGA, and then it will delegate the SHA3 to the FPGA. So one of our goals of the workshop is to understand how that will happen, and that's why we'll be mapping SHA3, this algorithm to FPGA later on on one of the days, and we will be doing emulation on that processor to verify whether the SHA3 algorithm is properly implemented or not, or it has been interfaced with the software properly or not. And we will be doing verification with Verilog using Embedded UVM on our server for the same algorithm. Okay, so now some implementation details of the SHA3. We won't be discussing details of the implementation in that sense, that we won't be going into the algorithm. Uh, just for a brief background, all the encryption algorithms are based on a concept of mathematics, which are called one-way algorithms. So basically, one-way algorithms are you have input, and that input gets converted into some output using an algorithm. And if it's one-way algorithm, it is as tough as almost impossible to convert back the output into the input. Okay, so a very small example, and by the way, that forms the basics of encryption, is if you have two very big prime numbers, and if you multiply them to create a very big number which has only two factors because you multiply two prime numbers, then from that very big, say that's a 500 decimal digits number, and you started with one 200 decimal digit number and another 300 decimal digit prime number. These two are prime numbers. So after you create that 500 digit product, it's very difficult to find out what were the two prime numbers at the input. Okay, so similar concepts are used in any encryption algorithm. So with SHA3, we'll give an input, it will give you an output, which is encrypted form of this input, and that output then is difficult to convert it back. So our SHA3 has 4 modes. Okay, so what are the 4 modes? The 4 modes are here: 224-bit hash, 256-bit hash, 384, or 512-bit hash. All right. So depending on how difficult or how tough the encryption is to break, you will choose 512 will be the most tough, and 224 will be not as tough, but slightly lighter on the algorithm side. So it won't take too much time to encrypt. Okay. Now our implementation, the implementation we have taken for verification, it's using certain registers, and all these registers, by the way, are read-only registers. So there's no control path in this SHA3 algorithm. The control path, typically, if you have control path, then there would have been a register which would define whether the SHA3, what mode of SHA3 you are using, whether it's 224 or 512 or anything in between. Okay, so that mode is decided in the data path itself for SHA3, as we'll see later. But there are registers which are read-only registers. So you have name 1, name 0, and name 1, which are, you can see the offset is increasing by 4. and that's what would happen on any memory mapped bus. The addresses would be incrementing with 1 byte. So it's a 32-bit bus, therefore the increment in address is 4 bytes. So if you have one register, that would be at 0, and the other register will have an increment in address by 4, because there are 4 bytes in 32 bits. So you have name 0 and name 1, and in these 232 bits, you want to store the name of the implementation. So typically, this kind of thing is useful for writing drivers. Okay, so when you are doing a piece of hardware, then when the computer or the processor wants to detect what kind of hardware it is, so you will have certain registers reserved for the name of the hardware. And actually, in many cases, instead of just name of the hardware, it will also have some ID for what kind of hardware it is, and some ID for who is the vendor who implemented it. Okay, but this being open source project, so there's no vendor. There's only the name of the hardware. So typically the ID of the hardware, so that the processor can recognize which driver to load, and then it will, or how to deal with that hardware. So then it will have a version, because version also is important for the drivers. What driver version is required for what version of the hardware, and then there are control and status registers. So we don't really need to go too much into name and version, but there is some functionality in the control and status register. So control register is telling you, so 30 bits of the control register are don't care, and that's typically how registers are in many hardware. So there'll be a lot of wasted bits, and there are only 2 bits which are of importance. And yeah, sorry, when I said all the registers are read only, I was wrong. There's one register which is write register. So we'll be controlling the hardware through this. So there is a little bit of control path, but we don't control the mode of the SHA3 as we work on it. But we have a little bit of control path, and we have 2 bits. So 1 bit is where we want to signal that it's the start of a new frame. I'll discuss the frame, what frame is in this protocol, in how we deal with the SHA3 from the software in our case, or from the hardware if another block is using it in an SOC. So we have a signal, and then we have we have a signal in it uh, which will represent or it will, when asserted, it will mean that I am starting with a new frame, and it will have a next. So next will basically tell the hardware that this is the next subframe of the frame. Okay, so we'll talk about it a little bit more in the following slides. Then there is a status register. So when bit 1 is asserted, that means the output is valid. When the bit 0 is when the bit 0 is, again, it always reads 1. So it's not don't care in that sense, but there is no use of it. So we are using only 1 bit of the status register. Typically, this kind of status register could result into this is a register here, but in many cases you want to have, instead of this kind of bit in a register, it could be an interrupt to the processor, or this kind of signal could go to a DMA, which will transfer the contents, which will transfer the output uh, from the SH3 block to some memory block. Okay, so that the processor doesn't need to keep polling on whether SHA3 has processed the data or not. But again, with SHA3, because one of the goals of the design was to have an efficient hardware, the processor may actually be polling even in a real case, in a real world scenario, because hardware processes the input very quickly. if the same input was given to software for processing, it would have taken much more time for the processor. But here the processor transfers the stream of data into the processor, into the SHA3 block, and then starts falling for the result. And after a few clock cycles, it will get the result and it will read it and move on. Okay, then there is data space. So there is space for the processor to write the input string into. So you see at 200, there is a block of memory where SHA3 will take in the input, and it doesn't consume the whole block from 200 to 300. The whole block, the whole address space, I would say, uh, would be 256 bytes, but the input that is required from at the input of SHA3 is only 200 bytes long. Okay, so it takes 200 byte, and that's a subframe. So the input being given to SHA3 could be very long. It could be, in kilobytes of data, but so that's the input phrase, but it needs to be broken into subframes, which can be at max 200 bytes long. And there is more to it, which we'll see in the next slide. So then we have the first, okay, sorry. Then we have the state, which starts at 300, and that will be the memory location from where we read back the result from SHA3. Okay, so starting at 300, we have only read only because we are reading back the output. So there is no use of processor writing into that space, because that space is for the SHA3 algorithm, which is implemented in hardware. In our case, for that hardware block to write into, and it will write the result of the hash algorithm, and then the processor will read from there. All right. So there are four modes, and we will see how the four modes are just for if you are using 224 mode or 256 mode, or in terms of bytes, it will be 20 byte mode or 28 byte mode or 32 byte mode, and so on. So what mode we are into will be decided in the way we give the input data. So it's not through a control register, but it's part of the data flow itself. So what happens is the SHA3 input, which can be of arbitrary size, and therefore it can be even in kilobytes, it's broken into subframes or blocks of 200 bytes. And depending on whether you are depending on the mode you are into, a part of the 200 byte long memory that you are giving in the input will be kept empty. Okay, so for example, if you are into 28 byte mode, so you will in that case be having a part of the 200 byte subframe. So the 28 into 256 bytes will be empty. And in case you are using 64 bytes, so you are into 512-bit mode, in that case, you will be 64 into 2, 128 byte will be empty, because 512 is where encryption is stronger, and therefore hardware will be taking more time. So hardware will be taking in data slowly. So it takes only 200 minus 128 bytes. That means in case of 512, it will be taking only 72 byte of data in one subframe. Okay, so the number of subframes, the number of 200 byte subframes is going to increase. But in case you are having 28 byte mode, that means 56 bytes will be reserved and 0 will be put here, and that will mean 144 bytes of data you will be able to give in one subframe. So the speed of execution would be double. Okay, because instead of 72, you are able to give in 144 bytes of data in one go. Okay, in one subframe. So it's not one clock cycle. It will be approximately 200 clock cycles that will be required to write data into SHA-3 for one subframe. But when you are doing it for for in 28 byte mode, then you are able to give in 144 bytes of data, which will be processed. And when we are using 512 bit mode, which translates to 64 byte mode, then you are able to give in only 72 bytes of data in one go. So as you can see, this is, slightly a layering of protocols, because uh, we are going to use Avalon members for putting data into the SHA-3 block, and the sequence that we have in the beginning, it's only a stream of data. So we have an array which contains the string to process and create the encrypted hash. But then in between, we have to have another layer which transforms that continuous string into frames or subframes which are 200 byte long. Okay, and then the last subframe will be special, because last subframe, because your data which is coming at the input may not be a multiple of 72 or 144, or in some other cases, for example, in 32 byte mode, it will be 32 byte, so 64 and 64 would mean um, you are left with 136 bytes. Okay, so in any of the modes, chances are that the input string you want to give in is not a multiple of that many bytes, and therefore the last subframe which goes in will have extra empty space, and still it needs to be distinguished from another input where the extra empty space was actually zeros, and therefore you have to distinguish it from that you know kind of input. You put a delimiter over here, and that delimiter is 06, and you did put a delimiter at the end also, which is 80. So still there'll be a special case where the input extends to actually this where I have this 00. So this blue portion extends to this 00, and this delimiter and the other delimiter, they overlap, and in that case we'll have that special case will be putting only one byte and putting both the delimiters in that one byte, and it will become 86. Okay, so that's how this whole thing will be processing. Okay, so now we take a look at the test bench and we try to relate it with this block diagram where I have the architecture of the test bench. So we have a collector, we have actually two collectors, one at the input, one at the output, and then we have monitors and checkers. So actually, I have kind of, there could be some difference in the architecture here. So there'll be two monitors. So it's this input will not be going into the monitor, which is reserved for output. So there'll be two monitors, and then from the second monitor, we'll be going to the checker. All right, and the checker needs to have a reference model in this case. So we picked up the reference model also from open source. So there is a tiny SHA-3 algorithm, which is open source implementation of SHA-3. And then we compare the output from the software and we compare the output from the simulation right now. And when we put the whole stuff into Cyclone 5 board in another session, we'll be comparing the output from the FPGA against the output from the software algorithm, which will run on the HPS part of the cyclone fire. Okay, so that will make, in a way, it will make emulation possible, a small scale emulation, a prototype emulation, and in another, the other learning will be how to put hardware onto the FPGA and access that hardware from Linux and make use of it along with your mainstream software. So we'll be learning FPGA based accelerators in that sense. Okay, so another pattern you will see here is SHA3 hardware implementation is open source, as well as the software implementation we have taken, that too is open source. So with the hardware accelerators, FPGA based accelerators becoming more popular, you will see this pattern getting repeated more often. You will have hardware which is open source, and you will have software which is open source. All right. So I move on to my Linux machine over here, and just to have less cluttering on the shared screen, I'll just share my Linux VNC thing. Okay, so I'm on a Windows machine, and this whole thing is running on another server, which is a Linux server. So I'll open Emacs so that we can browse through some code. Okay, so this is the directory where we have just give me a second. So this is a directory where we have the simulation run. So there's a separate directory where we have the RTL, and there is a separate directory called test bench where we have the test bench. And as we saw inside the source directory, we have, in addition to hardware, which is RTL, we also have test bench. Okay, this is the unit test. So the designer will write some tests just to make sure that his design is working, but this is not very extensive testing. Okay, so as we saw, for example, we had special case where the last frame could be extending to the last byte, and the two delimiters or the escape characters were overlapping. And instead of 80 and 06 separately, they were becoming 860x86. So the unit test may or may not be covering that special case. In our case, we'll see it doesn't cover. Okay, so a more thorough testing will want to cover all the special cases. And since you don't want to leave this exercise to the human intelligence, modern verification environments run with the concept of randomized testing so that we can cover as many special cases via random test cases as possible. So modern verification environments will have random test cases, but then in addition to that, human intelligence will be used, and you will have some special test cases which you will manage either through directed test cases within the UVM environment, as well as by way of putting constraints. So we'll see how to do that. Okay, so we want to put constraints in such a way that the special test cases are handled. All right. So let's go into the RTL first. We'll see a little bit of how the RTL is organized. And I also want to show you something special, and that is this is open source, and this is released on a website in a GitHub where a lot of other encryption algorithms are also released open source. And you can also see the details I had given you earlier. This was competition, the CACHEC competition, where this implementation got selected. So it was a kind of, basically uh, the 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 people, the institute or the organization which wanted to uh, have a good hardware and software implementation, an algorithm which can be used efficiently in hardware as well as in software. So that organization had a competition, and these were the winners. There were some winners, and a lot of other if you just go through the README in the parent directory that I've created, so the README will have the details of where I took this design from. Okay, so this is the place I took it from. So you can find a lot of SHA2 implementations and other implementations on the same website, and you will be able to, if you want to have another open source hardware, encryption hardware for your own projects, if you want to do something yourself in test benches or in RTL, you can see a lot of open source hardware there. This is the place I took the software implementation of SHA3 from. And then we need at least a version 10.2 of Icarus Verilog, which we have already downloaded, and Embedded UVM. We want to use all this to verify it. Okay, so then in the source, you will find the RTL. The RTL itself didn't have, wasn't using, a proper standard interface. So it had a memory mapped interface, but it wasn't um, employing any standard. So as you can see, it had ready, next, in it. All these were signals, and this will be typically the case where this kind of stuff will be used in SOC environment, because having these as signals is probably more efficient than having registers to give input, or to give control signal which is in it, or having to write another register to give that you are to basically tell the hardware that you are using the you are inputting the next frame. So but since we wanted to put this whole thing into an FPGA, so we wanted, and the FPGA and the processor will have only a memory mapped bus to do that. So even these control signals, we had to kind of encapsulate them into registers, and that's how we are using them. So the ready signal, which is coming from the SHA3 algorithm, is an output wire, and this also we are having as a status register, which the processor needs to poll to find out the whether the processor, whether the SHA3 algorithm has completed in hardware, and the output is ready or not. Okay, so this is the interface which is originally there in hardware. And since the people who created this open source hardware wanted to use it in some ASIC, we can't take this because this doesn't um, this is not a standard interface, which is a memory map, a bus based interface like AVMM or AXI. So we put a wrapper over it, and that wrapper is here, this one. Okay, we put a wrapper over it and made it into clock reset, chip select, write enable. So this is a proper memory mapped bus. So and then we created registers for input and output, both for control and status, as well as for uh, inputting data for the data path. Okay, so this file, as you can see, okay, we didn't create this file. This is again from the same people who created the hardware. Sorry about some misunderstanding there. We created this file, which is an Avalon wrapper. So whatever memory mapped bus they had over here, um, we created another wrapper on top of it to make it compatible with Avalon. Okay, so this is the file created by us to make it compatible, and so that we can put it onto the FPGA and interface it with the software. Okay, so my mistake where I said they were using this in the ASIC. they weren't using this, they were using the wrapper, and therefore all the registers, etc., are implemented by them only. Okay, so they have a status valid, which is still not a register, but the other registers have been implemented by them. So they probably were using this more as an interrupt. But then on top of that, we created another register for making sure that the status is available as a register only here. The status valid register. So we assign it to something here. Okay. So I'm not too comfortable with this RTL part because I didn't write it, but I wrote the test bench. So let's go over the test bench. So as usual, as with embedded UVM, we have two parts of the test bench. One is the BFM part, which we cover in Verilog, and this aligns very well with emulation or with FPGA kind of prototyping, because there also the BFM part gets synthesized, and the embedded UVM part will be done in a way that we work only at TLM level. So we work in embedded UVM only at transaction level, and then the transaction uh, is transferred to uh, the BFM via automatically written uh, PLI routines, and this is done very in a seamless manner. So the end user who is creating the test bench doesn't have to write these routines himself. These are written very seamlessly under the hood in embedded UVM. So this is the typical BFM for the memory mapped bus, the AVMM. I'll go through this in a little. Then you have two routines, these two tasks, read and write, which are getting used by this BFM. And then we are connecting everything. As you can see here, we don't have anything separate for monitors. So the same BFM is doing is putting data into the bus, and the same BFM is getting output from the bus. So this kind of architectures, let me show you. Give me a second. So this kind of test bench architectures, why this is not happening? I want to go back. Control Shift Alt F. Yeah. So this kind of test bench architectures, the driver in such a case is called duplex. Okay, so the driver gives input to the design, and then since it's memory mapped bus, there is no output separately. So in this diagram, for sake of having more space here, I have put it that way that I show monitor the output is coming on a separate bus, but actually it is coming on the same bus, because we only have one AVMM bus, and this bus, if we are reading on the same bus. If we are writing, we are writing on the same bus. So this becomes a duplex driver. So it writes, and then in case it's writing, the data will be written. In case it's reading, then it will give address, and it will give the corresponding control signals, and the data will come out on the same bus. Okay, so it becomes a duplex bus. You drive and you read back from the same bus. All right, so we'll see in the BFM how we are driving into the bus and then reading back from the same bus and giving it to the monitor. So let's see. So we take one item, and this item has address, it has probe, it has data, and the flag. The flag is whether you can see it here. The flag is, if it is 0, then um, it is read, or if it is 1, then that means it's write. Okay, so we have one flag signal which depicts whether it's read or write. So so you can see slightly how the transaction when it is in software is keeping that information in 1 bit, but on the signal level, this bit has to be 2 bits because there is separate read and write. Okay, that's how AVMM bus is. So we keep that information in software in 1 bit, and at the signal level we have to give it in 2 bits. So we have address, strobe, data, and flag. These coming from the software, and then we say if flag is 1, you write it. If flag is 0, you read it. Okay, and finally over here you are having the monitor part. So you have the read data which goes back into data, and then you put the transaction back. Okay, you you get a transaction, but you put it back here. In case of streaming bus, we saw how there were a separate BFM for driver and for monitor, because actually there were separate signals for giving input to the block and for getting the output from the block. So there were 2 separate streaming buses. Here there is only one bus, and that's the AVMM bus, and therefore the architecture of the test bench will employ uh, a duplex driver. So there'll be input, and the same driver, the same BFN will get you the output back. Okay, so that's how it happens. So most of the stuff is easy to comprehend. In the write routine, we put the address, we put the data, and we say that we assert the write at the postage of clock, and then it's done. It's basically done. And on the read, we put the address, we assert the write instead of asserting write signal, we assert the read signal, and we are done. Okay, so you can see over here there is a possibility of having both the read and write signals not asserted together. Okay, basically not together. They should never be asserted together, but none of them is asserted. So that will be one scenario. So in that scenario, the bus is idle. It's neither reading or writing. In certain other memory mapped buses, you only have one read write signal, but there is a valid signal along with it that neither read nor write is happening because valid is 0. In case of AVMM, we have read and write separately, but just to tell the slave or wherever we are reading or writing into, the master will assert neither of read or write. So that will be I don't have a valid address or data to talk to you. Okay, so that's how this part will work. And then you either read or write, and then you wait for the transaction to complete, because the slave could tell you that, okay, I'm not right now ready to receive data, or right now I'm not ready um, to give you the data wherever the read request has been, on whatever address the read access has been from the master. Okay, so this is also part of the AVMM bus protocol, that the slave could delay by asserting this signal. So long as the slave is saying, okay, wait, I'm not ready. So we'll keep asserting that data, whatever we did, the address and data, whatever we did in write or read routines or task. Okay, and then once the wait is over, we would just move on and collect the read bus, whatever it is, uh, give it back to the duplex driver. And when we do that, we also because we don't want to, whatever assertions we had done over the control signals here, and whatever address and data we had put over there, or the slave might have put on the data bus, we don't want to continue with that. So basically these read and write signals, we want to make 0 after the cycle is complete. So we do that, and we make the address and the write data bus, we make it X, so that in the waveforms we get a nice waveform with where we can understand, okay, the cycle, read or write cycle has finished. And then we also send back a signal to the test bench that the execution of this particular transaction is over. Okay, and then we put this transaction back into the test bench, so that the test bench can know, at least for the write data, for the read data, it can get that value. In more elaborate buses, sometimes you will also have error signals. I think those are there in AVM, AVM, AV memory mapped bus, Avalon memory mapped bus as well, but we haven't used those. So in certain, if the slave or the hardware you are talking to from your processor, if that hardware is more sophisticated, in certain cases, you can also get back an error that you wanted to read or write into a particular address, and that particular hardware says, okay, I don't have an implementation for that. You gave me a wrong address, for example. Okay, so I can't read or write into it. So those error signals should always be going back into the monitor. So even if you are writing data, there could be some signal from the module that your write has been completed without error or with error. So monitor should always be there, whether it's read or write. In our case, the slave is simple and it doesn't give you an error if you, for example, if you go back to the slides. So this is what I'm talking about. You go back to the slides, then here, for example, from 200 to 300, there are 256 locations. If you see, we only are using 200 locations out of this. So the rest of the locations are not implemented. So if you try to read or write into those locations, then if the slave is more sophisticated, will assert some error on the bus. Okay, so that part is not implemented for this simplistic slave. Similarly, if there is a read-only block, like we start from 300 onwards, where the output comes, that block is read-only. If we try to write into that, the slave should assert some error on the bus. So that we haven't implemented. That part is not implemented in the RTL, and that's why we are not taking those signals of the Avalon bus. Another small point, the input that we are giving is aligned at byte. It's not aligned at word, which is 4 byte long. It is aligned at byte level. So you could even have odd number of bytes. Okay. So, but in the when we are putting the input into the bus, then it is aligned at word because it's a 32-bit bus. Okay, so there is a strobe signal, and this strobe signal will tell you, at least for the last few bytes which are coming in, it will say that strobe signal will have corresponding only the corresponding bytes active. So strobe signal will be 4-bit long, and only the corresponding bits of the strobe will be asserted, just to signify that this is the last word and only a few bytes uh, are to be sent on to the slave or to the RTL. Okay, but okay, actually, what I said is not so true, because we'll always be sending the whole 200 byte data, but in some other cases that could be useful, but not in this case, because we'll always be sending 200 bytes of data. It's not that we send up to this, even zeros we have to write. Okay, So strobe will, all the 4 bits will be active for us all the time. But in certain cases, in Avalon bus, the strobe could assert only certain bits, so that it is trying to say that it's only a half word read or write, or it's only one byte read or write. Okay, but I'm sorry for the confusion there. In our DUT, will always be asserting all the 4 bits of the strobe signal. Okay, but that information is coming from the test bench, and in our case, all the 4 bits will be asserted together as far as the strobe signal is concerned. But the bus will still have that indication, because it's a standard bus and it has facility for the cases where you are doing half word or quarter word read or write. All right, so that much about the BFM, and then we go to the rest of the test bench. Okay. Um, as usual, we have a sequence item class in the beginning. We have put some constraints here, which are really not just for the sake of putting constraints. We are putting constraints. Okay, but obviously, if we are putting constraints, then those could signify that we want to limit ourselves to ASCII range or something like that, because with SHA3 in software, when somebody wants to have SHA3 hash encryption, the input is usually limited to ASCII string. Okay, so this is not exactly ASCII string that I'm putting as constraint, but you can find out what the ASCII characters range is, and you can put those constraints here. You have a phrase. The phrase length will be constrained as well, and I'm putting this constraint that it's from 0 to anything between 0 and 100 and 1024, so 1 kilobyte. Later, as we progress, after we understand all this, we'll change this constraint on length, and we'll put another constraint just to cover the test cases, just to cover the scenarios where, I don't have those slides visible right now, but we want to cover the scenario where the escape characters 80 and 06 overlap. So for that, I'll show you how we'll try to cover that through constraints by fine tuning the constraints. Okay, then we have a sequence. We have a sequence item, then we have a sequence. Okay, and this sequence, obviously, as I told you earlier, with sequence, most of the functionality is in body. Okay, and as earlier, we create a sequence item, we randomize it, and then we clone it and start it and finish it. Okay, so this start and finish stuff will be pushing this sequence into, we'll be pushing the transaction into the sequencer, and the sequencer will be pushing it into the driver. All right, so there's not much to the sequence over here. It just takes, it just randomizes the transaction and puts it across. Now, the interesting part over here is the transaction itself is not one AVM read or write transaction. It's a full phrase. All right. So the transaction, as we saw in case of that simple adder, we had made a transaction or a sequence item, and that was 1 byte long only. Here we are making a sequence item, which is the complete trace. Okay, because it's the SHA3 sequence item. So this SHA3 sequence item, later we will split it into multiple sequence items, which will be AVSD sequence items. Okay, so that's where that kind of splitting is actually what you call virtual sequence. All right, and in between, while doing that, we will also make sure that we create those 200 bytes long frames first, okay, so that the protocol which is required by SHA-3 is met. So right now we have the complete phrase. We haven't broken it into some subframes which are 200 byte long, depending on the mode that we are having, we are using. And if you look at the sequence item, which is actually another kind of sequence only, so you have outsize here, and this outsize is actually an enum, right? This is an enum, and this will be either 224, 256, 384, or 512. Okay, so when you randomize this enum, you don't have to put any constraint on it that it can be of these 4 values only. The constraint solver will know that it's an enum, and it will automatically find out, okay, what are the valid values, and it will put one of the valid values over there. All right. So then there is a path in this sequence. So the normal sequences, it will create random sequences and send you and send across. But there is a path where you can set phrase and thereby give a directed test case. All right. So because you are setting not only the phrase, you are also setting what mode it is of these 224, 256, etc. So you are setting that as well. So that's the path for directed test cases. And then you have a sequencer. As I told you, most of the meat of a sequence and sequencer combination is in the sequence only. Sequencer is mostly what you call boilerplate code. You have an agent. We'll talk about more about it later. But then you have Avalon specific. So a sequence item which is atomic, which kind of takes only one word of data which needs to be written into Avalon bus, and it pushes that into Avalon bus. So that kind of sequence item we have. So okay, let me do one thing, because this all may be becoming slightly confusing for people. So this is what we are talking about. We have SHA-3 sequence over here, then we have Avalon level sequence over here. Okay, so this is the virtual sequencer I'm talking about, and this is where we'll also be doing uh, arrangement of the SHA-3 sequence that you're getting at the input of the virtual sequencer, and we'll be arranging those into subframes which are 200 byte long. We'll be inserting those delimiters, or you can call them escape characters, which are 0x80 and 0x06 respectively. So we'll be doing that logic here, and then we'll be sending it to the AV Avalon memory mapped bus, AVMM bus. Okay, so we'll be sending it to that, and then the BFM will drive it to the DUT. So that's how we go. We have a sequence item. We have constraints in the sequence item which will not be used in this case, because we wanted to have a generic Avalon sequence item which can be used independently also. But here it's these sequence items will be created in the virtual sequencer. So it's mostly a split or that kind of thing happening. So you have a long sequence and it's split into multiple ABL Avalon bus sequence items. So randomization doesn't happen here. So these constraints are there, but we don't use them. And then from here, since the things will be going to the driver, as I showed you yesterday, that happens very seamlessly in embedded UVM. So you don't have to write the PLI code yourself. It's done through these two simple interfaces. And as I told you yesterday, this put values is overloaded, not overriding is when you do it through inheritance. Overloading is when you have the same function name, but you have multiple signatures of the function. So for example, over here, I can, if my sequence item had more items, so I could have just pushed them along with the whatever I have. So all the sequence, all the elements are getting pushed this way. And just for recollect, this is what gets available in the BFM. So in the BFM, you have one-to-one match, address with address, stroke with stroke, data with data. This type signal is renamed as flag over here, but what is important is the the number of bits is same. It could have a different name, and the order is same. So address will go to address, even if we renamed it as read whatever AV address over here, but it should be in the same position. So this is how embedded UVM will talk to Verilog. Okay, so we are sending this sequence item to the design, and when we do that, we do it via PLI, and that PLI is taken care of under the hood. You don't have to worry about it, worry about those implementation details. And as we do that, the interface is very simple, that you have for every transaction, you just specify how the order of the elements of the transaction, how they are getting converted into signals over here. So you just give all the elements. This also is done because, you know, in Verilog, in plain Verilog, you don't even have plain old Verilog. I'm talking about, where you know, you had Verilog 200 2005 standard. So you didn't even have structures implemented, and therefore there was no way that you group uh, multiple variables together. Okay, so that's why we are forced to send each of the element of transaction separately and collect it in Verilog separately. So, but the interface is very simple. And then we have another sequence wherein we create those complicated 200 byte long frames. Okay, so you can see how we are doing it. We are first we are first calculating the rate. Okay, we are calculating this rate. So this will be 200 minus size into 2. So that's what we are doing here. 200, instead of 200, it becomes 1600 because we are doing it in bits. And the size also we are taking in bits. So size can be 512 to 56, etc. And then this is the number of bytes. So this is number of bytes which will come in the end because we are dividing by 8. Okay, and this we are doing this way because when we talk about size, then if you see normal terminology, people will not be calling it 64 byte encryption, they'll be calling it 512 encryption. Okay, so that's why we kept size as 512 to 56, etc. Instead of keeping it in bytes, we kept it in bits, because, you know, ultimately the whatever you are writing should be readable, and people are more accustomed to using size in bits rather than, when it comes to encryption, they're more accustomed to bits rather than bytes. Then we find out how many frames will need to be there, and then we create each of those individual frames, and finally we are putting uh, those delimiters in the last frame. All right, so we are having number of frames here, and if we find out that it's the last frame which is going in, so that's the test for that. Last data word, actually data byte actually. So we put that delimiter there, and in case it's also, it also happens to be not also, in case we need to put, so this is the case I'm talking about, putting 06 and 80, and you can see we are ORing here just to cover the case that this 06 and A0 overlap. So we are not putting equal to 0, we are putting odd with 80 so that we cover that special case. All right. And then we take that whole, you know, we filled in these spaces, and then we create that full memory block, whatever needs to be written into a VLL. So that whole memory then is get transferred into uh, into Avalon bus. So you see the virtual sequence here. The initial sequence just has the string, ASCII string, which needs to be hashed into SHA-3 using SHA-3 encryption. It needs to be hashed into either 512 or 256 or whatever the other standards are. So initially, we just have that input string as would be given by the end user. Then we have a virtual sequencer which converts it into blocks of 200 byte long uh, 200 byte long frames. Then each frame then is getting driven after you convert them into 32-bit words. It's getting driven into the DOT using the Avalon bus. Okay, so this is slightly complicated stuff. Uh, a lot of people would probably say that I shouldn't be covering this kind of complicated stuff in a 2-week workshop, but that's not the idea. The idea is if I was just doing the theory and not giving you the code, then you should say that this kind of things, this kind of complicated things should be avoided. But I want to give you code which you can reuse, and that's what happens in the industry. Such complicated stuff nobody writes from scratch. If somebody wants to write a virtual sequence, for example, they'll take another person's virtual sequence and modify it. You just need to make sure that you understand the concept. Then the boilerplate, you should never try to write yourself. You copy it from another place and modify it. Okay, so I wanted to give you something you can use for creating something useful which may have virtual sequences. So that's the the stimulus generation part. We still have something more, which is we still need to uh, in the stimulus generation still need to tell the design that we are starting with a new sequence, and then at every frame we need to tell it that this next frame is coming in. So all that is implemented here. I won't go into too much details. Okay, so these are kind of, you see, I'm creating directed uh, Avalon memory map level transactions, because this can't be randomized. The data we have already randomized, but these are control signals which need to be given along with the data. So these are not randomized. So I create directed uh, sequence items. These are transactions, and I call them as part of the sequence. Okay, so they are in the body of the sequence. So not everything in a sequence is randomized, and that's the beauty of there were earlier standards like you had VMM, which was another standard for verification methodology, which was not IEEE, it was a vendor specific standard. So those standards had sequences implemented as data. And then this kind of thing over there you will do in constraints. In UVM, they decided that instead of having sequence as data, sequence would be functionality. So which is a higher level of flexibility given to you. Okay, now you still may have data inside this functionality, but it's something which will this body will be, you'll be able to, instead of doing this kind of stuff through constraints, you'll be able to do this kind of stuff as a function. So it becomes more flexible. So the data part we are randomizing and giving here, but in the end, to start uh, the frames, etc., you are doing that stuff without any randomization, and you are giving directed sequence items for Avalon bus. So now what we still need to cover is the monitor part, and how the uh, scoreboard or the checker will function. I'll cover that, but before that, I want to, along with you people, I want to generate the frames. I want to run the test case. I want to generate those waves, and I want to have a look at those waves along with you people, so that we can put the things in perspective. So this will take another 10-15 seconds. So later on, let me switch on my video. So later on one of later sessions, this is the board we'll be using. We'll use the same sequence. Actually, the sequence is only 100, phrases getting encrypted. So that will be on a later date. We'll run something like 1,000 frames on this small board, and we'll see, instead of taking 20 seconds, it will take a couple of seconds. So um, basically a performance boost of 100 times, which is kind of very, very good for UVM test cases. I mean, if you talk to commercial emulation platforms, they'll have figures of 3,000 or 5,000 or sometimes even like um, uh, 10,000 performance boost, but then they are not running UVM test cases in most of the cases, because UVM test case itself will take a lot of time. In our case, this particular case, it's actually very good. We are not even using multi-core here. It's a simple processor, two-core processor. Therefore, multi-core can't get you too much benefit. We are not using multi-core, but in our case, the test bench is simple. There's not too many constraints to solve, and therefore the performance boost is good. But the other point is the test case is running on the same platform. It's not going via Scheme or other buses, and that's why communication between FPGA and the test case and the test bench is very fast, thanks to SoC FPGA technology. And therefore, we get a performance boost of 100, which is extremely good given the size of the design. Typically, if the size of the design is bigger, since simulation of bigger designs take more time, so for bigger designs, you are going to have better performance boost with FPGA based emulation. Okay, this is a very small design, and yet you get a very good performance boost. So that is one part. The other part is we are in addition to the thing that this can be used as a emulation platform, at least for modules of significantly complex um, implementation. But I mean, it can't be done, for example, for SoC level where billions of gates are there, but you have bigger FPGAs uh, from uh, from Intel, which can take, I'm not sure how much is the latest, but which can easily take up to 100,000 up to 100 million gate design. Okay, so that kind of complexity, if your IP is having, you can still do this kind of emulation and get good results. Okay, now going back, another another level of importance, or I should say another um, area where this kind of thing could be useful is where you are doing mainstream FPGAs, wherein you are actually using FPGAs not for prototyping, not for emulation, but using FPGAs for making algorithms faster. And you are actually using FPGA for putting your design there, and you'll be using the FPGA as an FPGA accelerator. There you need something where you can find out whether the design is actually working after putting it on the FPGA. So this kind of test bench which we do in embedded UVM can work actually on the SoC FPGA and make sure that your FPGA is working. Okay, so a kind of handoff between handoff from the RTL designer to the system level integrator who is a software engineer. So he gets to know that even after putting the design onto the FPGA, all the test cases are passing and therefore integration is perfect. Integration problem, a problem in integration could be, for example, in software driver, or it could be in the RTL at the FPGA. You'll probably need to create a wrapper for the FPGA implementation, and the problems could be in any of those areas. So to find out whether the integration is perfect or not, this kind of thing could be very useful. So we go over to the waveforms. So this VCD file has been generated. So GTK wave, and then AVMM, SHA3, VCD. All right. So the waveform viewer is up, and we'll start dumping some waveforms into this window. So we dump the Avalon bus. Okay, as usual, the initial part of the waveform is all unknown because the module hasn't been reset yet. So we zoom out and we look at the waveform now. Okay, so we have actually put in 100. So if I zoom out, so these will be the read, the wait request, not the wait request actually. Where is that signal? No, that won't be there. So we are just using Avalon bus, so there won't be any signal here which signifies that so it will be slightly difficult to debug at waveform level, because as we saw in AVST bus, there was a signal, there was an end frame signal, which meant that the whole sequence that you are testing has gone in. Here that signal will not be there because you are using, so you are actually mapping your sequence to Avalon addresses, and those addresses will, a particular address will mean when you are giving that init or next signal will mean where your sequence boundaries are. Okay, but here all the debugging will have to happen at the sequence item level rather. Okay, so you can see here, so there are multiple frames going in. Actually, if you look at the the whole waveform. So each of these read, the spikes in the read actually are multiple reads. Okay, so these actually give you an idea, a semblance of where the sequence is ending, because after writing, after I write, which is almost like continuous write in the zoomed out waveform. After I write, for every sequence, I'm reading multiple times to read out what has been the output from the DUT. So this is where I'm reading. So it's also multiple bytes, multiple words actually, because I may be reading 64 bytes, or I may be reading 32 bytes depending on what mode I'm using for encryption. Okay, so then you can, for individual transaction, you can still zoom in and you can see how the BFM is working. You have read, and since in a test bench you'll be using the negate clock instead of POSH clock because you want to have stable data at POSH. So you'll be using negate clock to give address, for example, and then you will assert the read signal, and the DUT will respond with data. Okay, and as you can see, this is a pretty good DUT. It doesn't ask you to wait. So it asks you to wait only when it is actually not ready with data. So it asks you to wait if I'm giving a read and at that time it's not ready with data. So it asks you to wait for some time, and then, so this is the wait, this is the only wait. So when it is crunching data which has gone in, it asks you to wait. If you were really dealing with a DUT which may not be very efficient, then at every write and every read, it may be asking you to wait because it doesn't have a good interface implementation. Okay, but this one asks you to wait only when it is actually working and crunching data, for example, over here. So it asks you to wait because this is probably a 32 byte encryption. So it asks you to wait for some time and then you read out the, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this is probably that 384 encryption where you are getting 384 bytes of data at the output. Okay, um, so there's not much I can discuss in the waveforms, just that this is how it works. Now we'll go back and we'll take a look at how the monitor part works. All right, so I'll maximize my window, my VNC window, then I'll try to find out if I already have the next window. Yeah, this is where. And then we want to see the scoreboard. All right. So for the scoreboard, we have this read hash. This is where it starts from. And we also would be having, this is the driver. So we'll see. So this read hash is getting called here. So after, because this is a duplex kind of driver. So the driver sends in everything, and then let me go back to the slides. So the driver sends in the whole sequence. Sequencer sends in the whole sequence through the driver to the DUT, and the driver is getting back after reading from here. So it's getting back some data, and that data is going to the sequencer as well. And in the sequencer, it is creating the sequence which has been read back, and then it will go to the monitor. That's how it will work. So it won't work through the normal collector. It will work via the driver. And this is called duplex kind of drivers. And why you want to do it this way is, like earlier I told you, in the normal test bench architectures, uh, did I cover? No, that I covered in some other slides. Where? Let me go there. Somewhere here. Yeah. So normally you want to do it this way. You want to have a driver and you want to have monitors which are acting independently. But here the bus is controlled by you, and since you are working with FPGAs and the processors, who will want SHA-3 encryption? Obviously, the software will want SHA-3 encryption. So it's the processor who is interfacing with the bus, which happens to be AVMM here. So instead of a separate monitor, we employ, and that will happen if you look at practically or in the real world, that will happen with most of the memory mapped buses, that drivers will be duplex. They'll take back data after reading from the PFM, and in many cases the drivers will take it back to the sequencer. And sometimes, for example, if you're doing register verification, then you have virtual sequence in terms of your uh, if you're having a UVM reg transaction getting translated to some kind of adapters there, so they'll be going back to the UVM reg package. So that's the full duplex driver kind of stuff. The full length of the stimulus generation is from the beginning to the end is duplex in those cases. Okay, so what I'll do is I'll modify these slides before passing them to you, because this is slightly confusing. I've taken the generic UVM architecture and mapped stuff, written ABL driver, etc. over there. But we are using duplex driver. So this collector is not there. This collector is also not there. Everything is happening through the driver, and it's going back to the sequencer. And so read hash function is called. So after generating those write transactions, you generate the read transactions. Okay, and those read transactions will be generated here. Here, this is the read hash function. All right, and then this is your driver. So then you have a monitor, and the monitor gets the data, and here process transactions. Right. Yeah. So the monitor is given data from the driver. So it's a duplex driver, and the duplex driver gives back data to the monitor. And then you have processing. So it's a lot of processing at the monitor as well. Okay. So because monitor doesn't even know the mode. So monitor has to find the mode in which data is getting processed. So it just, had all this happen through control registers, monitor would have been able to find out what mode, like 224 or 256, what kind of encryption it is. Now here monitor is able to find out, but only by analyzing the data. So it analyzes the data, and then it processes the data back into the phrase format, and then so here all that is happening. I won't go into details of this code because this is very, very specific to SHA-3. The workshop is not about SHA-3. But you get this code to keep, so you can understand it, you can ask questions if you have any. And then finally, after it has created, it has grouped those transactions into a complete phrase. It goes to the scoreboard. Okay, and in the scoreboard you then do this is SHA-3 sequence item, which is the original phrase that you have. And this is the aspect, this kind of aspects I want to discuss, because these are related to UVM. All right, so we have objection mechanism for determining whether a test case has finished or not. A lot of times this objection mechanism is in a way handled from inside monitors. Okay, because what will happen is you will have a stimulus going into DUT and then coming out from DUT either through this way or that way, and then going to the checker. Now, once the stimulus generation is complete, the stimulus generator will say, I'm done. But it's for the checker to see whether all the outputs from the design have been received, and the checker will also make sure, because from the input it is getting how many inputs have been there, so the checker will count that as many outputs have come out, because this DUT, for example, in SHA3 is still simple, in the sense that corresponding to every input it is going and giving an output right away. In case of networking chips, for example, there might be an internal buffer, and it takes in 100 transactions in the that router maybe, or whatever DUT it is. It takes 100 Ethernet packets in, and then starts giving out slowly, depending on how the analysis of packets has been, how after applying, say, quality of service and everything. So in those cases, the outputs will start coming out very slowly, and the input stimulus generator says, I'm done. But it's for the checker to find out whether the DUT has completed all the data crunching, and DUT has responded to all the inputs, and all those inputs are available to the checker. So in those cases, as well as for SHA3, because it takes a little bit of time for data to go in and then come out, um, you basically have this objection mechanism getting handled from the scoreboard. Okay, so you really count whether, so when we, like my initial implementation of this test bench didn't have objection mechanism in the scoreboard. So the last transaction I used to miss. It used to go in, but before it came out, my test bench will get over. I don't want that to happen. So then I improvised and I added objection mechanism inside the scoreboard. Okay, so it will be here, it will be in the stimulus generation as well. Okay, so in the random test case as well, but in the scoreboard as well. So test cases where the the inputs are getting generated, and there also you are raising objection. So you raise objection and then you drop objection. So corresponding to every raise objection, there has to be a drop objection. So you are raising objection in the stimulus generation, you're also dropping it, and you drop it here also after you have found that all the transactions have been completed. Okay, now this is one part. So I told you I introduced this objection mechanism later on. So I want to touch upon a subtle uh, method of working, actually, which is very agile. So it is like this is how you create test benches. So you don't create the whole stuff in the first place. So you start on a project. So it's not that you'll create the whole test bench and after that start testing it. You will want to create only initially, you will create only for example, the driver part and the sequence item part. Okay, and then you will make some part of the test bench working. There's no scoreboard, nothing. So you just want the BFM to work. Okay, then you will start slowly, you will keep adding components, and finally once you are sure, once you see that your monitors, drivers, everything is working, then you start working on the scoreboard. So this is called incremental development. Okay, and this will save you hours of debugging. If you don't follow this method, if you instead write the whole test bench first and then start debugging it, then there'll be a lot of rewrite and it will be very, very confusing. So you always want to incrementally write your test bench and keep growing it. So for example, My test bench, even after I had almost finished, it used to when you run the test bench like you run here. So in the end, I used to get only 99. So from the stimulus generation, um, there were 100 transactions which got generated, but in the log report, I used to get only 99. So that's when I went back and incrementally added something to the test bench. Okay, so and that's another place where embedded UVM excels, because in embedded UVM, when you are working on a test bench, especially if you are working at SOC level, then the test bench compiles within a few less than a minute, less than half a minute. But if you start working with system Verilog, for example, with big SOCs and even with, like I was working for a customer where even with incremental compilation, if you make a small change in your test bench, it will take 15 minutes to test that, because it will take 15 minutes to compile and elaborate your design again, and then only the design simulation will start working. So with embedded UVM, you get only half a minute. Actually, it is about 10 seconds for small designs. And within that period, the whole thing gets compiled and you have a working simulation. So this is where productivity improves, because you get to have, you can think of working uh, in a fashion that you are incrementally building your test bench in a very productive way. Okay, so going back, yes, we still were looking at the monitor. Okay, so there is only one aspect of monitor which I want to cover, and then we'll have a break. So, there's that tiny SHA3, which is a software algorithm. So I need to show you how that gets integrated. So this is the SHA3 algorithm. This is implemented in software. Just for reference, this is where that code resides, in the test bench in tiny SHA3. So you have a README here. You'll be able to find out where I downloaded it from and how the software is implemented. And there's only one C file and one H file, primarily because this is also this was one of the goals of SHA3, that both hardware and software implementations should be efficient. So hardware will be at least hundreds of times more efficient in terms of at runtime. Okay, so this is MIT license, and we don't invoke main, because main is something else. They're testing it. They're testing the software implementation in main, but we invoke SHA3 and SHA, the header file. So these are the files which are important to us. And if you see, this is so. Let me go into a little bit into compilation. So we have a make file, and in the make file, uh, when we just say make, then these are the targets which get made. Actually, when you just say make without any specific, without any target, then the first target is taken, and in our case, the first target is all, and meaning thereby these two targets, these two sub targets, we can say, need to be compiled, and this first sub target is here. So this is basically iVerilog invocation for compiling the design, as well as part of the test bench, which is the BFM. And this is actually my test bench compiled as the shared library. Okay, so this is how I compile it. So I need the test bench written in D, as well as I need the reference model. So the reference model will go in as a library, and my test bench, which is written in D, will get compiled, and this particular library will get linked in. So the compiler will get invoked. $@ in makefile will mean the target. So -OF $@ that will mean $@ will be replaced by the target, which happens to be the shared library in our case. We give -shared as a flag because we don't want to create an executable. We actually don't even have a main function because we are getting attached to a simulation. So we need to create a shared library. So that's what gets created. And then we given UVM library and the simulator and Phobos, which happens to be the D library. We use all these libraries for creating the test bench. And we also link in the Z3 library, which is the SMT solver from Microsoft. And finally, this is something required for, because, the simulator, or in our case, the simulator is Icarus Verilog. The simulator will be loading the whole thing as a dynamic library. So libdl is also required. And finally, we are giving $bow, and this will mean whatever the dependencies of this target are, and the dependencies with these two. Okay, so the library will get linked in, and the test bench will get compiled. Now, for the library, also the makefile will work because the library is also a target somewhere. So we're here. So the library still depends on sha3.o, which is the object file, which gets created from this sha3 file. So this is how the whole makefile will solve all my dependencies automatically. When I just say make, it will compile everything because these are the targets for compile. When I say run, then I still have the same targets because compilation has to be completed first, and after that the simulation will run. Okay, so that is one part. The other part is we still have to cover a lot in the rest after we come back. So we have to cover the design patterns, and that's where we'll start understanding this part. Okay, and we will also right now what I'll do is I'll comment out. I'll comment in, actually it was commented out. I'll comment in the objection part. Okay, and I'll run the simulation again. One thing is compilation will not happen because I haven't changed anything. I've only changed the way the simulation is run. So compilation won't happen. Okay, now you see so there is a lot of cluttering. The objection mechanism, how it is getting triggered whenever an objection is dropped or an objection is raised. All that is now getting into my log file, and I'm able to see that. So this is helpful whenever you are working with objections and your objection mechanism is not working properly. So you want to trace how the objections are getting raised or getting dropped. So whenever that you want to do that, this switch may be useful to you. Then this is more important, the verbose debug. So what we'll do is we won't have the objection one, we'll have this one. So I'll still comment out objection mechanism. So when you do that, so you see a lot more information, right? Okay, what I'll do is I'll kill this simulation. I need to say finish. Okay, because when I kill the simulation, the Verilog simulator still keeps working because the control interrupt doesn't Linux interrupt doesn't go to the simulator. So it goes into debug mode. So I need to say finish so that it comes out and I can interrupt the simulation. Now I'll run the same simulation again, and I'll uh, redirect the log report into a file. Okay, I can do it in two ways. One is I can redirect it completely, or I can T it. T will mean it will go to a file as well as it will be displayed on the screen. So I'll T it, and I'll call the file avmm log.txt. Okay, so it's visible here, and we'll be able to open the file later in an editor. So it will take another 15 seconds. Yeah, it's done. Um, yeah, so I open the file. Tab. All right. So I open the file and I open the log. Actually, the file I need to open. So this is the file. So now, since I enabled debug, you can see a lot more messages started coming in. This is my original sequence that I'm printing. So since it was a long sequence, it didn't print everything. So that's some fine tuning in UVM, where by default it will, if it's a big array, it will only print the first 5 and the last 5 elements of the array. Okay, so it is giving you all the information. It's a phrase, which is an array, and then the different elements of the array. Then you have out size. So it is even giving you the value of the out size as well as the enum string corresponding to the value. Okay, and it's telling you what's the size of the particular field. It's telling you the size of the various bit size of the various elements of the array. It's telling you the size of the array. There is another field which is whether it's read or write. So it's telling you the size of that as well. Okay, then this is the request is an object. It's the sequence item. So there's an ID of that sequence item. It prints that. Okay, so then you have a lot of other messages, phase mechanism, which phase it is entering, because you have enabled debug. Okay, and then after the phase mechanism, because phase will be very active until the simulation actually starts. So once those phases are taken care of, then you will see more of sequences and how the sequences are getting executed. Now, all this is coming because the phase mechanism is part of the UVM. So they add some debug messages inside UVM so that you are able to debug it better if you enable debug in your log reports. But when you are writing a test bench, then at certain places you can yourself say debug. Okay, so this is normal UVM info. So if you see where all I'm calling UVM info, I'm calling at many places, and sometimes I'm saying medium, sometimes I'm saying debug. Okay, so that is the verbosity level. Normally, I just want to have this message which says that my input has been matched with the output. But at certain places, I want to enable debug so that if something is not working, I can just enable debug in my log report in my simulation run. And then I get those extra messages. So this is one feature in UVM which allows you to debug. Now, there is slightly I'll talk about embedded UVM here as well, because this is important for what we do on the boards. So if you see, if I'm doing this medium kind of thing, I can even okay, one more thing. So if I run a simulation, and in the simulation, in the make file, instead of debug, I say none. So instead of debug, I say none here. I say none. Okay, then even those messages will not come. The usual messages will not come. Where it's typing that some particular basically whatever the input sequences are, so those are getting matched. So it gives a message for each one of them. So those messages didn't come. So I just ran a test in a non-verbose mode. And this is totally clutter free. I'm able to, because say if there were errors, then those messages where the things are getting matched, those would have cluttered the errors as well. So here I just get to see there is no error. All right. In case of error, what will happen is instead of UVM info, I'll use UVM error. Okay, so I need to see, oh, I'm searching in a make file, so that's why the search was unsuccessful. So I need to go into the test bench and I need to look for error. So in case things are not matching, I'm making transactions. So either some protocol is not getting followed or things are not matching. So this is where I'm finding problems in the frame itself. So then there'll be an error. And in case, so this is also frame error. So protocol is not getting followed. This is not the AVST protocol. This is the protocol where the after monitoring, those 200 bytes are not in the right format. Okay, so this is illegal address error. This is illegal address. This is mismatch error. Okay, in case finally, after I get a sequence and I also apply my software as a reference model, then I check it against expected. If there is a mismatch, then that's an error. So in case there was an error, and there were lots of infos like the cluttering we had done earlier, then you'll really have to go back and see where those errors are. So you will be doing a lot of more manual stuff because you'll be searching for errors. So best is to not to enable any kind of uh, info messages by saying you don't want any infos, by saying verbosity equal to none, and then only the errors will get displayed. Now, something I wanted to add about embedded UVM here. So let's see. When you are creating an info, okay, so now, so I'll just open that file. So when, for example, this info is getting created, okay, this is a debug info, but even if it's debug info, it gets created. So for every line, there is a lot of formatting which is going. This string is getting built, and then it is getting displayed on the machine, on my console. So if there are a lot of debug messages, even if they are not getting displayed, so when you say UVM info and you give this verbosity in UVM gets applied at the end. So this format, etc., will anyway happen, right? This format will happen, and the whole string, whatever is there, will get, for example, this debug string. This is read. Yeah, this info. So I'm printing the error into a string. Now this print will happen irrespective of whatever the debug is, whether I'm actually printing the debug information or not. This line will get executed and this print will get called. Okay, so this is what happens in normal UVM, in system Verilog UVM. In embedded UVM, since we'll be running it also on these small boards, and where the RTL simulation is not happening, and therefore RTL is running on FPGA at almost zero time. So in embedded UVM, we have a technology, a software technology called lazy computing. So this actually will not even get executed in case debug is not there. So it will be skipped. So actually what will happen is this particular part will be passed on to the lower UVM info function as a function itself. So it will be wrapped into a function and it will get passed on to the lower level functions, and where that comparison is happening, whether debug messages have to be printed or not, there it will be decided whether to call this function and actually create the print a message or not. Okay, so that is one technology which is available only in embedded UVM, and it again for most of the test benches. I mean, this is not my data. This is data from EDA companies. The log reports in many test benches can take as much as 50% of the test bench execution time. So we are saving completely on that. So we get a 50% boost just because of this lazy execution of functions. Okay, so with that, what we'll do is we will finish this session, and then when we come back, I'll take you through the design patterns, which is very important for, again, understanding of factory and other stuff. And so it's already 12:10. We come back by 12:40. And by 12:45 sharp, I'll start the session. Okay, so I'll come back by 12:40, but by 12:45, I'll start the session. So please be in time. So between 12:40 and 12:45, I'll take a few questions. Thank you.
Thank you, sir. Yeah. So the participants, I will request that sir will be taking all your queries post lunch. So you all please join us sharp by 12:40, sir, or
Yes,
12:45?
12:40. 12:40,
Yeah.
I'll take a few questions, and then
Yeah.
12:45 we can start.
So we will be addressing all the question at 12:40, and we will start the session by 12:45. So please, all of you get connected with us by 12:40. Thank you, sir.
All right, so I'll take a couple of questions. One is somebody is asking about what UVM warning reports are. So basically, just like you have UVM info and UVM error, there is another level where you can say UVM warning. The difference between UVM error and warning is mostly like a flag, which is, you know, it's there's a difference in uh, severity of the stuff. So error is actually, you want to say error whenever there is some functional error in the DUT or in the test bench, then you want to say error. But just 1 minute, there is a message. Let me read that. Yeah. So primarily, there is a difference in severity. So UVM warning is more like UVM info because it's not an error. And UVM warning typically doesn't mean the test case has failed, but something which the test bench wants to tell to the verification engineer, which cannot be masked. UVM info can be masked. For example, um, you can have UVM verbosity to a level that you mask away UVM info, but warnings cannot be masked. On the other hand, UVM is very flexible, so there are even uh, ways to tell UVM that it should a particular kind of error. For example, you can, so in UVM you can even categorize errors, and in a particular test case you can even say that that particular category of error should be upgraded to warnings. Okay, or I shouldn't say upgraded, but downgraded to warnings. Upgrading basically means increasing the severity. So you could even tell in a particular test case when you are running it that all the warnings should be upgraded to errors. So it's more like, you know, it's a way to tell you the severity. That's all. All right. Um, and then there is a question which came to me by email where somebody, not email, on WhatsApp group, where somebody is asking me, can we find out delay power consumption of the DUT? Yes, in the sense that though embedded UVM connects with the DUT via at transaction level via those you know, VPI calls to get a transaction from the BFM to the test bench or vice versa. But when we do that, we copy the timestamp as well, and we synchronize. So if you see a typical run, okay. So I'll just open the make file. So I'll open the make file. There's no Emacs right now, so I'll open the log file actually. So I open the log file. So you will see there is a timestamp while I run the simulation. So this timestamp is the actual simulation time. So when we communicate with the DUT simulation, we actually also transfer a timestamp and we synchronize the test bench, the embedded UVM test bench with the DUT timing, and that's how these timestamps are coming. Okay, so this will be in picosecond. This will mean so many picoseconds. That will mean if I leave out three most least significant zeros, so these many nanoseconds. So the simulation has moved to 602.68 microsecond. So that way, so we can get the delays, and the similarly, if you want to get these delays in the scoreboard, so you should just copy the timestamp. So in system Verilog, for example, you have $time to get the timestamp. In embedded UVM, you have get time, and that way you can get the current timestamp, and you can copy it into the monitor. And along with the transaction, you need to have an element in the transaction to hold the timestamp, and you can then do whatever processing of time you want to do. All right. So having said that, I would like to move to the slides. And actually, there is a lot to cover right now in the slides. So we haven't even started with the slides, whatever we wanted to do. All right, so we'll be covering design patterns today, and there are basically these design patterns that we'll be covering. So actually, first for some background into, okay, I'm not sharing my screen, so let me do that first. So yeah, my screen should be visible now. So let me tell you some background of what design patterns are, and then we can continue. So basically, when object-oriented programming started, basically when typically you had C++ and Java coming into life. So I'm talking about the early years of object-oriented programming. So this pattern movement started a little bit before the Java came into life. So that should be in 1990s, early 1990s. So what people found was that there are certain when you program, there are certain patterns, and those are the patterns of software architecture. And if you follow those, then you can write better software. So this kind of idea people got from building architectures. Like for example, there is a book on building architectures which talks about building architecture patterns. For example, one of the patterns is if there is a seating arrangement in a room and the seats are such that the only window in the room is on your back when you're sitting on that seat, then the person sitting there will feel uncomfortable because he doesn't have a window view. So therefore, the building architecture pattern suggests that if you want to have a seating arrangement in a room, then keep it in such a way that people who need to sit there should have the view of the window in some way. Like they may have to tilt their head sideways, but it shouldn't be on the back. So from there, people got idea that even in software architectures, there are patterns. So there are ways to program which make software programming better. And there are ways in which if you program in that way, then it will make your program very hard to maintain. So those are called anti-patterns. So there are patterns and anti-patterns. So there are typically 23 main software architecture patterns. Okay, there are 23 of them. We'll only be covering 6 of them. Actually 7, because factory pattern is 2 patterns combined into one. So there is discrete factory pattern and there is abstract factory pattern. So without wasting much time, let's go ahead and see what these patterns are about. So I will start with template method pattern. So template method pattern is nothing but the dependency inversion principle. And basically, it's one of the software patterns. High-level modules should not depend on low-level modules. Both should depend on abstractions. Abstractions should not depend upon details. Details should depend upon abstractions. In order to conform to dependency inversion principle, we want to make sure that generic algorithms do not depend on detailed implementation. So something we do in UVM or embedded UVM all the time. So I'll show you some code examples and we can follow from there. So for example, whenever we write, and we'll take a simple example. So whenever in a test bench, maybe MNIT, not this file. So this is the file. So whenever we write a sequence item, it will have some fields. So these are the fields, right, of this sequence item. There is type of sequence item. In this case, the type identifies whether it's a um, whether it's a 224, 256, 300, 84, or no, that's the outside, sorry. So excess enum, so whether it's a read or write. Okay, so basically I want to have the same sequence item for the output as well as for the input. That's why I keep a type over there. And then there is a phrase being being an array, and then there is outsize. Outsize basically tells you whether what kind of uh, string you are inputting, what kind of, actually not string, but what kind of uh, encryption algorithm you want to make, how strong the encryption should be. So these are the three fields, and except for type, the other two are randomized. Okay. Now, similarly, if I just search for UVM default, so you will see it here. In the AVL sequence item, there is address, data, and type. Okay, again the read or write type, but there is address or data, and then there is probe also. So what we'll do is, um, so we have this sequence item in the driver, it's getting played here. So request is of type this, and what we'll do is, whenever we are putting a request to the BFM, before that we will print it. Okay, so what will we need to invoke UVM info, and then we need to have a tag to this info, and we'll say AVL transaction. So this is the transaction that is getting played on the BFM, and then we need to give this transaction. So we'll say request.sprint. All right, and then there has to be some verbosity. So we say UVM, and here we will say none. So even if somebody is giving none as verbosity in the filters, so it will still get printed. Okay, so I'll make my window maximized, and then after saving this, I say make. All right, so then I say make run, and that way all my transactions will display. Okay, now how the transactions are getting displayed, so we need to go into that a little bit. So these transactions, because I added a UVM info, these transactions are getting displayed. So all I had done was, every time there is a transaction, I say UVM info, and then I display that transaction by this UVM info command. Now this request was of type ABL sequence item. And this is where I defined ABL sequence item. And in ABL sequence item, I haven't specified anywhere that how what are the fields which should get displayed, and like for example the constraints are not getting displayed. And then if you what we should do is we should give this run into say log file. So I'll name that abl.log, and I'll open that. So the same thing, if you do it in system Verilog, it will happen the same way. And see, the log file is very big now because all the transactions are getting displayed, and it's taking slightly longer to run it. Now, if you see, address is getting displayed, data is getting displayed, and these are all hex numbers. Type is getting displayed, and since type is also an enum, it is displayed as enum as well as the hex number. Then strobe is special. It is getting displayed as binary. Okay, and then because it's a transaction which is getting played uh, on the DUT, there is also a begin time, and there is that begin time comes from when we have that sequence body. Inside sequence body will say start item and end item. So that timestamp is noted here. So we'll see later on this timestamp will be incrementing. Okay, so this is the timestamp from the simulation. All right. Now, what is particular out here is that strobe is getting printed as binary, while and why we print it as binary, because this is kind of a flag corresponding to each byte of data in the data field. So each byte is represented by one bit, and what we are actually writing into the ABMM bus, the strobe is related to data in that sense. So we want to see individual bytes, and that's why we are printing it as bit level data instead of hex data. Otherwise, it would have been F, and then finding out which particular bits are enabled or not will take some manual effort. All right. So how it is getting printed as all ones instead of just F? So how it is getting printed as binary instead of hexadecimal is because of it's because of this specification over here, that it is bin, UVM bin. All right. So you are specifying that strobe should be printed in bin format, but there is also default over everything, on top of everything. So in D or in embedded UVM, when you put an attribute on a block, so it gets attached to every field. Okay. Now, so the point is that you are attaching UVM default to every field, and anyway the rest of the information is there. For example, the information that this is of enum type is there, whether this is of address width will come as a parameter from somewhere else. So how many bits are there in the address, that is also coming, that information is there. Similarly, this is this is probe width, so this is 4 in our case, and data width is 32 in our case. So all that information is already present. So on top of that, we are adding information that this has to be printed in binary format. Okay, but this is only data, this is only, attributes available. So there must be something which is actually printing it. So all that happens through something called UVM object utils. So UVM object utils, when you mix in embedded UVM, and actually it's a macro in system Verilog. So macro is also something where the code will get copied in a way. That code, whatever the macro is, will be copied into your class, and mix in D is also works that way, that this code will be mixed into your class. Okay, so there is some code coming here, and that code is defining the copy, clone, byte pack, byte unpack, and a series of related functions. You call them auxiliary functions. And those functions are actually looking at whether your particular field is what's the type of the field, what's the like when you say UVM default, that basically means that field needs to be printed. It needs to be, if there is a byte pack function, that field will be byte packed. So what if, for example, if I take this particular parameter and put it outside? Okay, so I put it outside. The whole thing will still compile and run. So the compilation will take place, and after that, it will also run. So all that will go into the log file. So this time you will see address doesn't get printed. So if you go down, scroll down, then when you see other fields are getting printed, address, data type, everything is getting printed except for address. Okay, so whatever those functions are which are coming, which are automatically made available to you by way of mixing in UVM object utils. Okay, so there those functions are making sure that if you have UVM default attribute, if you have that attribute, then you are just a minute. Only in that case, your particular field will get displayed on the screen, which will get printed if you are printing that particular transaction. All right. So having said that, so this information, UVM default information, gets attached to address as well, and therefore it gets printed. Okay. Now there are other. So UVM default means we want it to be printed. We want it to be cloned also, in case we are calling clone function. So uh, these macros, whatever is defined in UVM object utils, will make sure that copy function, clone function, byte pack function, byte unpack functions, all those functions get defined. And those functions are based on the attributes that are available on a particular field. In System Verilog, it's slightly different. In System Verilog, you would be defining all these fields separately. Okay, and then instead of this, you will be saying UVM object utils like this, and because it's a macro, and then you will say begin, and then you will say, you will list each one of these fields again, and thereby you will say, because you want to put, you want to tell the compiler that what kind of attributes you want to put to address. So you will say UVM field, UVM int field, and then you will say address, and then you will say UVM default. So System Verilog has this slightly verbose way of doing the same thing. In embedded system, in embedded UVM, we have something much better because we are directly attaching attributes to the field rather than through macros like that. Okay, so in System Verilog, you have to make sure that you have to define these macros for each of the fields separately. So what will happen is, in case you miss it for one of the fields, then that field will not be displayed if you are debugging. That field will not be copied if you are copying. That field will not be byte packed if you are calling byte pack, and that will be source of many errors, right? Having said that, I started showing you all this stuff is because I want to explain the template method. And the template method is that you will define in the derived class, you will define functions, and these functions will be called in the base class. Okay, so let's see how. So we go to embedded UVM implementation, and there embedded UVM beta 7, that's what I have. And there I go to import, and then UVM, then base classes. And there you will see UVM object, and there you will see a function called do print. Yeah, do print. So this is the base class function do print. All right. So by way of putting or mixing in UVM object utils, this function will get overwritten, and there'll be another function which will actually print these elements. So it's actually slightly different. There is a different function instead of do print, which makes that happen. But that's the idea. Like in the base class, there'll be a virtual function, and you override it and create the details in the extended. So this is the generic function. And since the generic functions, generic class, generic base class, so since the generic base class doesn't have any elements, so it won't print anything. But when you extend it in the extended class, you will have the details depending on what kind of transaction you are creating. Okay, so then when do print gets called, it actually prints the elements of the class. So that's what template template design pattern is. So similarly, you will see for all other sequence items as well, like for SHA3 sequence item as well, I have mixed in UVM object utils. All right. So thereby all those functions will get defined. And over here also I have mixed in this we already saw. So these two places we have mixed in. Okay. So we can just search for mix in as well. Here as well. Then there will be every component will have UVM component utils. So this is having UVM component utils. So all the component specific um, methods will get automatically defined. All right. Let's go back. So detailed implementation depends on the base class in the sense that the base class will tell you that it needs a do print function, or it needs a function which lets it know how to copy various fields and stuff like that. So here is an example in a simulator, and this is all software, so it may not make so much sense to you, but in a simulator, the simulate function is a top level function. It's a higher abstraction function, and then it needs lower level functionality, which is next event or schedule event. And there can be two kinds of simulators. One is calendar type, the other is priority type. So those detailed implementations will actually define the next event and schedule event function. So actually The simulate function should be defined only in the top level simulator. It shouldn't be there in the derived classes. And the simulate function calls these two, and these two are virtual function in the top level class in the higher abstraction layer. But depending on what kind of simulator it is, the definition of the lower level functions, next event and schedule event, will be different. But the top level function will be defined at the top level, and it will also have protected functions, protected virtual functions, which can be overridden later. All right. Um, the simulate method is fully defined in the base class simulator. Depending on the chosen scheduler algorithm, implementation of next event and schedule event methods get picked up. So that's about template method. Just as a layman's example, I can say when you fill in your income tax returns, so you get that Saral form from comment. So that's like template design pattern, because the form itself, whether you get it in a paper format or you get it as a Microsoft Excel template, so the form itself has the higher level algorithm of how to calculate your income tax, and the lower level details of what your income has been, what and basically other details like whether you have done some certain savings which allow you to have income tax rebate. So all those details you fill in, and then the higher level algorithm is not in your control. It's decided by the government in the template itself, and that gets called, and your income tax gets calculated. So that's a typical template example, template pattern example. All right, and then you have the next pattern, which is a strategy pattern, which is different from template method pattern only in a subtle way. So template method pattern uses inheritance, and strategy pattern uses delegation in addition to inheritance. So strategy pattern uses delegation for solving the same problem. And so strategy is usually like more it's applicable at more places. So now just to give you another example, so we saw how a basic income tax calculation is done through a template pattern. Now another example is if you want to calculate GST. Okay, so GST rates depend on the particular whatever services you are providing. It depends on that. Then it depends on if you are making a purchase or a sale of products, then what kind of product it is, it depends on that. All right, so if you are creating a GST software, then each of the product will have a way to identify whether GST is applicable on that or not, and the product will have a GST rate as well, and then the kind of sale or purchase has been made, that will also define whether it is interstate or within the state, and therefore whether interstate GST has to be calculated, or it is you have the state and center components. Okay, so so now you are delegating the calculation of GST on the particular activity, whether it's a sale or a purchase activity, or whether it's a service, whether you have hired some service or you're providing some service. So depending on that, GST rate will be applied, and depending on that, the GST on that particular activity will be calculated. So you see the subtle difference. In case of income tax, the whole thing is dependent on me. And in case of GST, I'm delegating it to the activities, that okay, for service This is the activity, and this is the GST tax which has to be levied, whether I'm providing a service or I'm hiring a service, so that will be uh, levied accordingly, and so on. And then the total service tax will be calculated. So in case of strategy pattern, it's delegation. It's delegation to the activities in case of GST, or it's delegation to the components of a class. And then on every component, you will be calling certain functions, and that's how you will be solving the problem. So the same simulator example, now instead of having next event and schedule event, inside the simulator itself, I instead have a scheduler component. And then I inherit from that component to define priority scheduler or calendar scheduler, and it becomes a strategy pattern. So strategy pattern uses delegation and hence allows more flexibility with the scheduler algorithm. It is now possible to choose the scheduler algorithm even after a simulator instance has been created. Okay. Otherwise, in the template method pattern, you would have to create a priority simulator or a calendar simulator. So at the time of creation itself, you'll have to say which one of these is to, because this is the base class which is abstract. It doesn't know the details of certain functions which are next event and schedule event functions. So this is abstract. So you'll have to decide in the beginning itself. But in case of strategy pattern, you can decide that later. And you even have the flexibility that at runtime, when simulation is running, in case, through artificial intelligence or something, you find, okay, this scheduler algorithm is not working good, I should have the other scheduler. So you can destroy this scheduler and create another scheduler and continue with the simulation. Then we have the facade pattern, and facade pattern is very simple. It's actually a more abstract pattern compared to strategy and template design patterns. So the facade pattern is used when you want to provide a simple and specific interface onto a group of objects that has a complex and general interface. So for example, the PLI interface in Verilog simulator is, so whoever wants to interface with a Verilog simulation will have PLI interface. So similarly, in verification methodology VMM, you have a byte pack function, and in UVM, you have a pack function at various levels. For example, you can pack at word level, or at byte level, or at bit level. So all those functions are available, and these functions provide an interface function between the different layers of verification platform. So let me explain it a little bit. For example, you have Ethernet, different layers of Ethernet, in the networking. So you have MAC layer, and then you have TCP, IP, TCP, and other layers. And actually, instead of IP layer, you could even have UDP layer. So so the MAC layer will be there. Then you'll either have UDP or IP. Then you'll have TCP and other protocols. Okay. Now for this kind of layering in network, mostly what needs to happen at a layering level is that the upper layer, for example, if it is TCP layer, the whole of TCP packet will be packed into uh, a string of bytes, and it will form the payload of the lower abstraction layer. For example, TCP packet, the whole packet will become payload of the IP layer, and IP packet, the whole of it becomes payload of MAC layer. Okay, that's how layering happens in networking domain. Now, when that happens, Sometimes you don't know whether upper layer will be IP layer or UDP layer. And in IP layer as well, it's not necessary that you are going to have TCP packet. It could be some other kind of packet. Okay, so you don't know what is going to happen there. So what kind of packet is coming from the top. So with uh, all that needs to be done in the lower layer is just to pack that. So earlier it's a class object which is having various fields, and those fields, for example, in IP layer, there will be IP address, IP source address, IP destination address, and some other fields. It's not a very simple packet. So all those fields need to be packed in a particular manner, and then they become payload of the lower layer. Okay, so this is how facade happens. This is how facade pattern helps there. That irrespective of what kind of packet it is, what kind of I should say payload it is, the lower layer will just call byte pack and be done with it. Okay, so that function will always be this single function, irrespective of whichever whichever kind of packet is coming from the top. You just call byte pack, and that's the facade. And you create the payload, and then the lower layer packet has a payload, and it becomes complete. So it may actually be calling CRC checksum on that payload, and then the whole formation of packet is complete. All right. Now, facade in general life, it will be, for example, uh, if you visit an organization, there will be reception in that organization where you will go and register yourself before you can meet anybody. So that reception will be facade of the organization. And similarly, if you are, say, you are buying components from a semiconductor company, then the salespeople in that semiconductor company, the sales team, will have accounts in the sense that they'll have an account manager, and that account manager will be catering to me every time I go to that sales company, that semiconductor company. Okay, so my account will be with some account manager in that company, and every time I go, he will be the one who deals with me. So that's like single interface. Why? Because he may have given me some discount on my earlier visit, and next visit, if I meet somebody else, he the other guy may not know what kind of discount has been given to me, so there'll be confusion. So that's why best to have one single interface for a particular client, and that's what facade pattern is about. Then comes the singleton pattern. Most objects are dynamic. Multiple objects are created and destroyed in the life of an application. But there's examples where some objects are not dynamic. They are singleton. Okay, so sometimes the class object might be static, might be of static nature, and it needs to be created right when the application is started, and gets destroyed when the application is closed, and there is only a single instance of such class required. So examples are UVM root, UVM printer, UVM. Then there is some class for tracing, log tracing. I'm forgetting its name. So all these are, even UVM factory. All these are singleton. So there is only one instance. So we'll see some code here. So this is how singleton is implemented. So in a singleton class, typically this code is in D language, the base language of embedded UVM. So if you're using embedded UVM, you'll be writing a singleton this way. But actually you don't need to write, because all the classes that need to be singleton in UVM base class library, they have been made singleton already. But in case your verification architecture requires a singleton component or something like that, so this is what you will do. You will make the constructor private. You'll make the constructor private, because if you allow people to create new objects of this singleton instance, then the purpose is defeated. People can create multiple objects. So you make it private and you make a function available, and that function will return an object of the class, and you will keep an object of the same class. So this is the singleton class, public class singleton. S should be capital here, so that's a typo. So public class singleton, and then inside there is an instance which is a copy of the singleton object. So you keep one copy, and then by default it is null. That means it hasn't been instantiated. Then the interface you provide to the end user, that's a function called instance. And when he calls instance, if instance is null, that means it hasn't been initialized, then the constructor will be called. Okay, now this constructor is private, but since this method is part of the class, so this private constructor, this method is able to call. Okay, and if in case it's lying null, then it will create a new instance. Otherwise, the next time it is called, this null will not be, this condition will not assert, so to say, and then the previously generated instance will be returned all the time. That's what singleton pattern is about. So singleton forces a type of contract obligation on the class client, that every time uh, the client calls gets an instance of the singleton class, it will be the same instance. So no new instance will be created. Now comes the factory pattern, and this is one of the more difficult patterns to comprehend. So remember the dependency inversion principle. We said that you won't depend on the lower layer. The lower layer will depend on the upper layer. The upper layer will not depend on the lower layer. Okay, so the principle asks you to depend on an interface instead. So upper layer will have an interface which won't change, and therefore we are reducing bindings, because bindings are only when something changes that will create a binding. But if something is not changing, then that binding is ineffective even if it is there. The problem is how to create an object of the class. So let me explain. So for example, you had so this is the upper layer, shape is upper layer, and the implementations are square and circle. Okay, so now dependency inversion says that shape will, for example, have a function called draw and a function called area. So this is the interface. Draw and area in shape are the interface, and they are implemented in square and circle. All right. Now, I'm saying that since there is dependency inversion, so anybody who wants to access shape will be able to say shape dot whatever shape he is having, he'll be able to say shape dot draw, and the draw function of the particular shape will get called. Let me bring some reference to what we had done earlier. So earlier we had the session layer where we were defining logon function, and logon function was in turn uh, calling dial, send, receive, and hang up, all these four functions. And the logon function will call these functions on a modem. And then you don't know which modem you are working with. So that's how you are creating, that abstraction level where the upper layer is not dependent on the lower layer, but upper layer is irrespective of what kind of modem it is. It just needs to call dial, send, receive, or hang up these functions, and then it's the responsibility of the lower layer that all the kinds of modems will have all these functions implemented as virtual function overrides. Okay, so now the idea is that the upper layer is is not having any binding with the lower layer, in the sense that irrespective of what kind of modem it is, you just need to call dial, hang up, or send or receive. Same thing is happening here. The shape, the upper layer, which is maybe a canvas. So the canvas doesn't need to say what kind of shape it is. It doesn't need to consider what kind of shape it is. It can just call draw, or it can call area as a function and be done with it. Okay, so the implementation details of the lower layer don't affect the upper layer. But now the problem is, when you are calling the constructor, then you just can't say, give me a shape. You will have to say what kind of shape it is, because shape is abstract. So constructor can be called only on discrete, not on abstract, but on discrete classes. Okay, not discrete. Better word will be concrete. So they can be called only on concrete classes. So square is a concrete class. It's not an abstract class. A circle is an abstract is also a concrete class. Shape is an abstract class. So the virtual functions can be called by the client by just saying shape.draw or shape.area. But the client can't say create a shape, because it will have to say what kind of shape it is. Okay, so it will have to say create a circle or create a square. Okay, so if I take it back to the modem example, I'll be able to call dial, send, receive, as well as hang up functions only after a modem has been created. But at the time of creating a modem, I'll have to say what kind of modem it is. So that defeats the purpose, because at that time I'll have to say whether it's a Haze or Courier or any other kind of modem. So as soon as I say that, that means if a new modem is getting added, then my upper layer is also getting changed, because of the change in the lower layer, because a new modem has been introduced. The upper layer has to know what kind of modem has been introduced, and it has to create an instance of that modem. So whatever we had achieved by way of dependency inversion is kind of lost at the time of creating an object. And that's what we want to now work on in the factory pattern. So let's see how. So this is the factory pattern. So what I'll do is, this is the upper layer shape, and then this is the lower layer square and circle. Okay, so I'll have a factory. And it will be called shape factory. So shape factory will have two views, so to say. There'll be a shape factory which will be abstract. There'll be a concrete shape factory. That's why factory pattern is the sum of two patterns: abstract factory and concrete factory. So this is the abstract factory and this is the concrete factory. So in the abstract factory, I will have functions like make square and make circle. And so I'm not actually calling the constructor, and the constructor gets called. So these functions, which are make square and make circle, they are abstract right now, and in the concrete class they get defined. And when they get defined, the definition actually is creating a square or a circle. Okay, so that way I am removing the dependency on square or circle, right? Because I'm not calling the constructor directly. It's in the client, which is at upper layer, gets to see only the interface, and the interface has abstract functions, and those abstract functions have definition in the concrete factory. So the abstract functions will not have any dependence on square or circle. But you can see I'm kind of lying here, because if in addition to square or circle, I also have triangle which gets introduced now, then I'll have to make a modification here, which will be make triangle. So though I'm not directly calling the constructor here, but there'll need to be a modification. So let's see how to remove that modification as well, how to take care of that. Okay, so I don't have a slide on that, but I'll have to say that. So what happens is I'll actually only have one function, which may be named make or create or whatever. So say I have a create function, and that create function takes a string. The create function takes a string, and that string could identify whether I'm making a circle or square or triangle or whatever. Now, since it's a string, so I don't need to, every time I add a shape in my lower layer, I don't need to create another function. I'll just say create square, create circle, create triangle, and that information is getting passed through that string. All right. Now, since it's a string, that flexibility is there, that what kind of object is getting created. So every time there is somebody adding another kind of shape in the lower layer, I don't need to have another function. So it will be create, and then it will have an argument and the definition. So it will be an abstract function here, the definition of function. So it will get overridden in the lower layer, and the lower layer actually defines create. And then the lower layer when it may do some comparison, for example, that the actual uh, the actual string that is getting passed to it, it is reading square, so create a square. If it is reading circle, then create a circle. If it's reading triangle, then create a triangle. That way. But every time a new shape is getting added, I don't have to modify any code in the upper layer. The upper layer code remains same. Okay, and then once the shape is created, I can call any function on it, which is defined in the shape interface in the base class. Now, how it is implemented in UVM, what UVM does is, in UVM, every time you define a new class, so you will be mixing in that code. Okay, you will have, I'll show you. So every time you are, for example, defining a sequence item, you say mix in. Yeah, in the embedded UVM code. So you're saying mix in UVM object utils. So the code which gets mixed in will do a kind of registration for me. So in system verilog, I'm just writing the code here. In system verilog, you will be saying tick UVM object utils begin, and therein you will give SHA3 sequence item. Okay, and then you will specify the different fields and what are the kinds of the fields. Here, I just need to say UVM object utils. In system verilog, for example, when you give UVM object utils begin, along with that, you also pass the information about what's the name of the class. Okay, and this particular, the particular macro which gets invoked here, it brings in something called factory registration, and this class gets registered with the factory. Now what that registration is, I'll explain that. But in embedded UVM, you don't have to specify the name of the class because embedded UVM is based on D. And in D language, I can do code introspection. So I can find out where these utils are getting added and what class I'm inside. So I can find out the name of the class myself inside this code. Okay, that can't happen in system Verilog because there is no introspection available. Now, therefore, I'm able to register this class with the factory. Now, what does the class registration mean? So let's go back to the slides. So when you say a class gets registered, what happens is every class will have a name. Okay, so for example, UVM, the SHA3 sequence item that I was creating, the name of the class is SHA3 sequence item. So what the concrete factory layer or the registration process in that layer is going to do is it's going to create a hash table. It's going to create a hash table. Hash table is nothing but an associative array. And the key of that associative array is the name of the class. Then it is going to actually create an object of the class and keep that in the abstract, in the hash table. So let me write some code here. So what will happen is, open another file. So the registration process will be something like this. There will be a variable, and that variable will be UVM object. And then inside that, because it's a associative array, so inside that a string. Okay, and then that hash table. So let's name that UVM factory or UVM register hash, UVM object register hash. All right. So UVM has a similar variable. So it may not be named same, but a similar variable. And every time a registration happens, registration is through call to some macro, and that macro will do UVM object what's happening? UVM object register hash, it will add an element to it. So in case we are dealing with SHA3 sequence item, it will add this item to it, and it will say this equal to new of SHA3 sequence item, and then it has to give a it has to every UVM object constructor needs a name. So it will say something like over here, the instance name will be, because it's a factory registration, so it will give it a name, say something over here. So name, whatever. The name doesn't matter for us right now in what we are doing. Okay, so a new element has been registered in the hash table. Okay, so now when somebody calls create and he calls create for, or he invokes the factory for SHA3 sequence item. So this information that it's a SHA3 sequence item is available as a string. Okay, so let me not confuse by calling the function create here. So let's call it factory create. And then it is called with SHA3 sequence item. All right. So this function, when it is called, it will make a lookup in the hash table. And when it makes a lookup, then it gets this variable. Because this, not this variable, this object. Because this object was created and kept safe there. All right. So I get that object, but it's still the same object every time. Every time I'll call factory create. So it's gonna be the same object. I don't want it to be that way, because if it's the same object which is coming from the factory, then it becomes singleton. I don't want it to be singleton. So what happens is the factory create will then call clone function on this object. And the clone function will create another object and give it to me. All right. So for example, I have this class aesthetic3, and inside the class I create a clone function. So I'll have a constructor first, this, and I'm using the terminology. So in D, the constructor is called this. So I have a constructor and I have a clone function, clone. And actually, we can avoid some confusion here. So it will be UVM object. All right. And here it will be base class will be UVM object. All right. And this clone function calls the constructor. So it says return, and then it calls the constructor. So it calls new. So though the constructor is named this in D language, but when you want to invoke and you want to create a new object, then you just say new. Okay, so it says return new. Now, given an object of this type, which has been kept in the factory register, and when I retrieve it, I can just call clone on it, so long as in the base class, I have a virtual function named clone, UVM object, and I name it clone. And this is a virtual function. It may not have a definition. And this is an override function. All right. Now, since the base class UVM object has a clone function, so in the factory register, I have kept an object of the actual class that was getting registered. So I have kept an object safe there with that string identification. So now when I'm accessing the factory, I just give this string. That object which had been registered will get returned. And if I call clone on that, since it's actually an object of this type, the clone function will actually create a new object and return to me. Okay, so this is how the factory will function. It will do registration, and when it does registration, there is a string association with the with that object which is getting which it's keeping safe, and this string becomes available to me later, and now I'm able to with a string, I'm able to say what kind of class I want to create, what kind of class object I want to create. So I'm removing dependency between two layers. And actually, now I'll be able to even specify from my command line what kind of uh, what kind of object I want to create. Okay, otherwise, if I don't register with a factory, then command line from command line I can't give, because command line will you will be only be able to give strings, not object types. So slightly, though I can't see your faces, but I know this is slightly an advanced topic, so it may not comprehend. You may not be able to comprehend. Most of you may not be able to comprehend the details in the first go. So you can revisit what factory is from a video recording or from my slides, or even on the web. You can Google for it, but these are the details. So it is removing dependency between two layers, and thereby we are able to decide, for example, what test case to run from command line, and we are able to create factory overrides. So typically, I'll show you in the make file that we had. So we had in the simulation, we were specifying in the make file that this is the object, this is the test to be run. Okay, there could be multiple tests, but you are specifying which test it is to run. And this gets passed on because it's getting passed on from your shell. Actually, in the make file also, there'll be a shell. So from the shell, whether you pass it on from command line or from the make file doesn't make a difference. From the shell, this information is going to your simulation, that this is the test you want to run. And inside the simulation, then an object of this type will be created from the string itself. Okay, and at that time a factory will come into picture, because otherwise it won't be able to find. So let's do an experiment. Instead of random test, we'll say random, and that's it. Or just like we can have a small typo. There's no underscore in random test now. And let's see how it will compile and it will run. But when it runs, what kind of error we get. Okay, now we say make run. So there is an error. UVM fatal, requested test from command line, this not found. So then there is this warning. Reporter cannot create a component of type random test because it is not registered with the factory. Okay, so it invoked the factory, tried to create a test, but that test didn't exist. Now let's make another experiment. So now what we'll do is we'll keep it random test only, and then we will run it. It will run. Okay, now it is running. But now we'll go back, and what we'll do is we will go to the test bench, and we'll go to the area where, sorry, we go to the test bench, we go to the area where this particular test has been defined, it's here, and we'll just comment out this mixin. So say, I forgot to give this mixin, and as I already told you, this is this actually brings in the code which makes factory registration possible. So now I've commented that out. This guy is taking time, so I'll kill it and I'll finish it. So now it will compile again because we have changed the code. No, what happened? Finish. Didn't I save the file? I didn't save the file. That's why it didn't compile again. So now it will compile again. Okay, so it compiles again, and then when it runs again, the factory, because factory registration hasn't happened, it will tell you that random test cannot be run. So the same error, cannot create object of type random test. The same factory warning, cannot create component of type random test because it hasn't been registered. It is not registered with the factory. Okay, so this is one use of factory where you are able to give the name of the test from command line. There are other uses of factory where you can do more subtle stuff, wherein, for example, you can do factory overrides. For example, in case you are running a test where a lot of Ethernet packets are getting created and you are testing some network domain DUT. So now with this kind of subtle changes, what you can say from the command line would be that instead of creating normal packets, create jumbo packets. Okay, and you have already created a jumbo Ethernet class, which extends from Ethernet class. And then when you say it from the command line, the factory, wherever it is creating a component, an object of type Ethernet packet, instead of looking for Ethernet packet, it will do the string registration. You remember the factory invocation is always through a string. So instead of creating an Ethernet packet type, it will create Ethernet jumbo packet type. And the whole test bench will now only be having jumbo packets because those are the ones the factory is creating. And that's why in the code, wherever you are trying to create something, you use create instead of using explicit new, because new doesn't invoke factory. Create invokes factory, and at the time of invocation of factory, it looks for overrides. All right. So if an override has been specified, then the factory takes a bypass. It won't create objects of this type that you are using right now, and it will override that type and give you object of the derived type, and that will get used. So the two use cases of factory, one is you are able to specify the test case name from the command line, and the other is you are able to override the kind of objects which will get created and get used in the test case. So what I'll do is on Monday, I'll have a slightly extended example where I'll explain how factory override works. So I'll have that example ready and we'll be able to run it. All right. So given that, now we go back to the SHA3 example and we cover a few things which we had left earlier, but yeah, even before that, we have to complete our design patterns. So I'll go back to those slides first. So we have factory, and we understood how a factory works. So a factory pattern is often split into abstract factory and concrete factory patterns. There can in fact be multiple concrete factories corresponding to an abstract factory. There are often other reasons to apply factory pattern. Creation of objects might be quite complex and elaborate functions for some classes. So the other reasons are normally, you do like when you write a class, then you have constructor within the class. But in certain cases, the construction of the class object may depend on external factors. That's when instead of leaving the construction of class object on the class itself, you take it outside and do it inside a factory so that external factors may modify it. And that's one example which I gave, where overrides, we are able to apply overrides on top of a factory object creation. So does it solve rigidity? Of course it does, because we were able to separate out layers. Here, I'm asking this question because in the slides, I don't explain how it works, and I still had dependency on these two functions. So in the slides, that leads to why there needs to be a better solution. I already told you about the better solution, which is hash-based and which is implemented in UVM. All right. So I'll give you a factory example on Monday, but let's go to the next pattern now. And that's another difficult pattern uh, that's called the observer pattern. We still have half an hour, so which is good enough time to cover the pattern as well as whatever is remaining in the SHA3 test bench. So now the observer pattern. So many of us would have been to the train station or to the airport and or to a metro station, and there we would have observed how there are multiple displays. Sometimes there are advertisements, sometimes just a simple clock, but all the clocks in the airport or all the clocks on a metro station will be completely synchronized, even their second limb, the particular uh, stick which tells you how many seconds have passed. Even those, just give me a second, there's a phone call. Okay, sorry for that. There was a phone call. So now, when we are, the example I was talking about, so if you are at the airport, so there'll be multiple displays, for example, each of the display will be displaying the same advertisement throughout the airport. And then that advertisement will change, something else will come. So it's not like, it's not like, uh, at least in case of clocks, it's not like a TV which is just uh, displaying whatever signals it's getting, because the seconds, uh, arm of the clock is changing in a synchronized way. So this is done through something called an observer pattern in software. Okay, so let's see what happens. So we have a digital clock and a clock. Actually, the clock is a software clock which is incrementing seconds, and digital clock is the one which displays it. So there might be multiple digital clocks, but there'll be a single clock. So there might be multiple instances of the observer, but the observed object is only one. Okay, so now what happens is the clock will, every time there is an increment in time, it will have a new data to share with people. Now, if a digital clock, for example, keeps asking the clock what is the time, then it will be more like a polling solution. That digital clock is continuously asking the clock that, okay, give me the most recent time, give me the most recent time, and clock keeps returning that. So that's how, you know, you could have visualized this a solution to this problem, but that's not the optimal solution. So what happens is the clock will be, this is the concrete class, and it will be inheriting from a base class, which is the subject. You have an observer, the observer observes a subject. That's why I'm naming it an object, a subject. So it inherits this interface from a subject, and the subject has a notify function and as well as a register function. Register function is public, notify function is protected, and clock will define it. Okay, so now an observer can get registered with the subject, and by way of that it can get notifications. So let's see how. Digital clock observes the clock. Clock registers digital clock instance and as observer. When time changes, a notification is sent to the digital clock. Digital clock updates time. Okay. So see, the point is, so let's take an example. Let's move ourselves to Mumbai, and there a lot of movies are getting made, and say we are all wannabe actors. Okay, we want to be a hero, and we are in the tinsel town, and we are looking for roles in movies. So one way is that I being, I need a role, so I'll keep calling one of the directors. Say, I don't know many director names, so say one of the directors, I don't know who, but I call a director, and I on the phone call I say I need a role. Okay, now what the director is going to respond is, I don't have a role. So next day I again call and I say I need a role. So again the same response will be there. And I'm only one of the wannabe heroes. There will be 1,000 people like me, and they're all disturbing the director. Okay, so all the time he's receiving calls that I want a role. Okay, so I'm this kind of I'm a male of this height and with blue eyes and with this kind of complexion, and this is my height. I want a role. All right. So every time he receives a call, he has to respond. I don't have a movie right now. I already have all the actors that I needed. So call me later. So that's one kind of system you can envisage. The other system is when you call a director, he says, actually, he won't even talk to you. He'll have some assistant or a voice message on a recorded machine, which will say, leave your phone number and your details with me, and I'll call you back when I need people. All right. Now, this is the registration process. Or he will say on that voice message, he will say, this is my email address. Drop your resume to me, and I'll respond when I need you. So this is an observer registration process. So he will have your resume or your details in his database. Then when he is creating a movie, he will look for people. Say he is looking for a person, for a male character with blue eyes, and he'll do a match and find out all the probable candidates, and then he'll call you. So observer pattern is, instead of observer calling the subject repeatedly, the observer registers himself with the subject, and then the subject calls the observer. Okay, so this is the pattern that we find in callbacks in UVM. And callbacks will typically be used for two purposes. One of the purpose of a callback, sometimes people use it like that, is for functional coverage. Okay, so you have a driver, and driver gives you a callback, and so you have to create a callback in the driver, and that callback, basically you have to create a callback in the driver means you have to explicitly in the driver, you with the driver you need to have a callback class, and then you need to have so a callback class will be instantiated or inherited from UVM callback base class, and then you'll have an instance inside the driver. Okay, now the observers, in this case an observer could be the functional coverage module. The observer will register itself, and every time there is a new transaction which the driver has received from the sequencer and it's going to give it to the BFM, the driver is going to send it to the callback, or everybody who has registered for the callback. And therefore, it will go to various components. It could be functional coverage, or it could be some kind of monitor. So they will receive this update that driver has a new object available, a new transaction available. Okay, so one is for functional coverage. The other reason people use callbacks for is something called error injection. So let's understand what error injection is about. When we did this SHA3, stimulus, then there was, let me open those slides so that we can have more clarity. So then there was a frame structure. Yeah, this frame structure. And the last few bytes of every frame needed to be 0. Now, there could be a case where by mistake, somebody gives an input to the DUT where this is not 0, where one of the bits or one of the bytes is not 0. So how will the DUT respond to that? Now, this may not be covered in the specification, but you still want to cover such cases because such kind of errors will happen, and that shouldn't bring an ugly side of the DUT in front of you. For example, in case you give such a input to the DUT may give a garbage result to me right away for this particular stimulus, but the next stimulus that I give to the DUT shouldn't be affected. Okay, so now this kind of stuff is called error injection, wherein, and this is not so important for SHA3 example, but for networking examples, it's more important. So normally in networking, you will have CRC checksum, and CRC checksum is only the only use for CRC checksum is that during transmission of the packet on the network, some error may not have crept in. And if an error or a bit toggle has crept in, my DUT should be able to filter out such packets based on the CRC checksum. Now, normally when you are testing a networking chip, you will give it a sense stimulus, you will give well-formed packets, but in certain cases, in certain stimulus, you also want to check that whether if in case there has been an error during transmission, then that kind of error, how the DUT responds to it. Okay, so that process is called, in verification, that process is called error injection. And a lot of time people use callbacks for such a process. So how will it happen? Callback will register itself with driver, and as soon as the driver has the new transaction, the driver will pass on this transaction to everybody who is registered. Now, the person who is registered will, or the code who is registered will modify the packet and introduce an error in it. Okay, and since when you pass on the transaction to the observer, you pass it on as a transaction handle. So it's mostly like in C, there will be a pointer. So in system Verilog or embedded UVM, there is a handle. So it's kind of a pointer going to the observer, and the observer is introducing an error in it. And since it's going through a pointer, the actual transaction also gets that error. And when it gets played on, this transaction is transferred to the DUT via a BFM, the error actually goes into the DUT. So a lot of times people use callbacks for this purpose, but in UVM, there is another mechanism of doing it, and that mechanism is via analysis ports. And you could as well use an analysis port to pass this transaction to, instead of a monitor, to an error injector, and that error injector sitting there through an analysis port, as soon as it gets the packet, it introduces an error. Okay, so analysis ports is simpler to use compared to callbacks, because analysis port is simpler to declare and use it for. With callbacks, you need to create a special callback class and introduce it inside your driver. With analysis port, you don't need to create an analysis port. You don't need to define it. You just instantiate it and start using it. So that's about observer pattern. There is a little bit more detail, and actually slightly over here, not here, here. So every time every time clock notifies to all the registered observers, the notification will be sent, and an update function will be called. So what notify will do is, notify will see who all are registered, and then it will call update function for all the people who have registered. And when it calls update function, it will also pass the current time to all the registered digital clocks. Okay, and digital clock through the update function will be able to display the updated time. Now, the principle that drives observer pattern is the OCP. So in OCP, what did we say? We said open close principle. What did we say? A class is open for extension, closed for modification, right? So if you are using OCP for purpose of a monitor or purpose of code coverage, then you are extending, but you are not modifying. But in case you are doing error injection, then you are modifying. Then you are taking a packet and you are making modifications. So error injection is a special case where you can do it, but normally this kind of modification should be avoided, because uh, there will be surprises. There'll be when your test bench becomes big, and some component in the test bench is modifying um, the sequence items, for example, which have been generated in the sequencer. So it will be difficult to even figure out who is modifying the transaction. All right. So use observer pattern, or even, so when you have analysis port and you connect monitors with it, so use it carefully. Make sure the monitors don't change the transactions, because otherwise you will be violating the open close principle. You are doing something to the, and actually the observer pattern dictates that when you are passing a transaction for monitoring, then you should make that transaction constant. Okay, so this is about scalability of your test bench or of your software. So you need to be careful if the test bench becomes very big, and in your monitors, for example, you are doing very simple things like which may seem harmless. For example, in a monitor, you could somewhere you could keep a count, and somebody is changing the count in the monitor. Okay, so there'll be surprises. The other components which are getting the same transaction will will not know who is modifying it, and when you get into a buggy situation, so you will be searching for what is happening and where it is happening. So use analysis ports as well as callbacks with some care. Don't modify the stuff unless you have a special case like error injection. So observed object stays closed for modification. In system Verilog, since the language does not enable constant objects, system Verilog doesn't even have, it has const as a keyword, but when it applies to objects, only the handle of the object becomes constant. The internal fields can still be changed. So in a way, system Verilog is crippled because of that. And there have been some debates on the internet on this, so you can search for those. Finally, open packages. So while classes in the same package exhibit strong cohesion, there's hardly any dependence between the packages. So you could have one package, you could have another package, uh, and inside the package you could have classes, and the classes may be calling functions from each other, but at package level, you should hardly have any interdependency. So for example, in embedded UVM, every class, every verification IP, um, my coding style at least is every verification IP will be completely defined inside a file. Okay, so if there is another verification IP, I'll create another file and I'll put it there. Now between these two codes, one code, and this becomes a package. And in embedded UVM in D, actually every file is a package in its own right. Though you don't need to declare a package, but it becomes a package. Okay, by itself, it kind of creates a package for every file. So in system Verilog, typical coding style would be you will create a file for each class, and then you will explicitly declare packages, and you will have certain classes inside the package. Okay. Now for example, the whole UVM base class library is inside a package called UVM package actually. All right. So while classes in the same package exhibit strong cohesion, there is hardly any dependency between them. So that's the idea of creating packages, that within a package, different objects uh, may be calling each other through functions and various ways. But between packages, there should be minimal interaction. So C++ doesn't have package construct, it has namespaces, which are different from packages. And but allows something called friend functions. Okay, so in case a class needs to interact with another class, then you make it a friend class. That's how you virtually create packages. So you will make, if you want to have multiple classes within the same package, and since C++ doesn't have the concept of a package, what you do is you have have the other classes declared as friends of this class, and that will create a virtual package. In system Verilog, you have a package. Okay, and but in system Verilog, all the data members of a class are by default public. but you have a package construct as well. So, but in system Verilog, the package construct also is broken. So that I can go into detail later on. I mean, if people are interested in knowing how it is broken, I can talk about it, but it is broken. And that's why people generally tend to avoid it. So it is broken in the sense, first of all, you can't have nested packages. You can't have a package and another package inside a package. So that is not allowed. The other point is, in system Verilog, you have, because system Verilog borrows heavily from Verilog and from C++. So you have this tick include. So as soon as you mix tick include with package construct, it becomes something unmanageable. So you could be including files inside packages. And if you have a package called A and you have a package called B, and you happen to tick include verification IP inside package A and the same verification IP inside package B, those two verification IPs become different codes. So a transaction generated, though it may be the same SHA-3 sequence item generated inside one package, will be incompatible with transaction generated inside the other package. So such problems in system Verilog will have made sure that people end up discarding package as a construct altogether, and they do stuff without declaring packages. In embedded UVM, we have good packages, and those can be used as required. Okay. So all this is slightly beyond what we need to cover, and I'll go back to the code. We still had a little bit left. So I want to explain how reference model written in C, they get included in embedded UVM. So we have this reference model in named, it's a C function. So I just need to declare this C function as extern C in embedded UVM. And then I need to have its signature. So this is the signature. It takes string as an input, and it takes string length as an input because it's a C function. It's not a C++ function. And then it returns me the generated hash. Okay, so I'm not giving it I'm actually giving it an array as input, and I'm getting an array as output. But these arrays are given as pointers. So this is what, if you open your reference bench, so you will find this function defined in the over here. So this is the SHA-3 function. Compute SHA-3 hash of given byte length from int. So int is an input, and then you give in length, and the output will be available in this array in empty. Okay, so this is how SHA-3 function is available for me in C. Now to integrate it, this is how I integrate it. So I just need to, so phrase for me in D is a dynamic array. So I can access its pointer because C needs pointer. So I just give its pointer to SHA-3. And then since it's an array, it will have a length. So in system Verilog, every array has a size as a keyword, but in D, every array has a length. So I give the length of the array to SHA3, and then expected is an array which I've already created with a particular size. So I give its pointer and size to the SHA3 function which has been written in C, and it will take the inputs, give me an output. Okay, and then I can check, I can have a checker which, so this is my reference model, and I get expected value from the reference model. I compare it against what is available at the output of the monitors, and then I either give matched or unmatched. So that way, because I used a ready-made reference model written in C, I don't have to write the reference model myself. And that should be the way, because if I write it myself, then the reference model may have certain bugs as well, and I'll need to debug those. But if I take it from a library or from somebody who has implemented and tested it, chances are I don't hit any bug. Okay, so this, and then the only portion which remains over here is the structure of the test bench. So you have monitors, you have test cases, you have driver, sequencer, everything. So now you have an agent and an environment. These are special classes in UVM. So an environment typically will have an agent, scoreboard, and monitor. Okay, and then an agent will typically keep um, the the stimulus part. So driver, sequencer, and monitor. The monitor, this monitor is on the stimulus generation part. Okay, so there's one monitor here. There's the other monitor which is on the output part. So whatever is getting observed in the output. So no, sorry, this is the low-level monitor, which is uh, part of the agent, and this I have kept here because it's directly related to the, I said it's a duplex driver, it's a duplex BFM, so to say. So the BFM part of the driver is duplex. So the BFM also relates to a monitor, and I put it here itself. And then the upper layer monitor is in the environment, it's in the environment itself. Okay, so basically, the point here is this agent is Avalon MM specific. So Avalon MM specific driver, Avalon MM specific sequencer, and Avalon MM specific monitor. Okay, so it pertains to a particular protocol, and then this becomes, in a way, the encapsulation of a verification IP. This verification IP is for Avalon MM. And then this agent, as well as the SHA3 agent. So SHA3 is the other layer, and I encapsulate SHA3 specific stuff over there, but there is only a sequencer, since SHA3 for me is only the sequencer layer. So that one also becomes an agent. Okay, and then you have a scoreboard and monitor. You don't encapsulate it because these are top level constructs, because you won't get a VIP for these, because uh, people don't know what kind of SHA3 protocol you are using and stuff like that. So uh, you won't get VIP for that. You'll make all these things yourself. AVL agent is a particular encapsulation which you can reuse across projects. So that's why you create an agent out around it. And then this environment will be encapsulated inside a test case. So test case in UVM is always the top level construct. You'll have environment inside it. So this is my test case. Inside it, I have environment. And this I explained yesterday in embedded UVM. We create the build phase automatically. So we just need to provide a UVM build attribute to the components which need to be built. In this case, there is only one component, but there are other cases where there are multiple components, like here. So there is no build phase. There's only we just attach this attribute. And then there is connect phase. I'll be discussing TLM ports, exports on Monday perhaps, or maybe on Tuesday. So there I'll discuss how all these connections and how data is transferred from one component to another. All those details I'll discuss. But for now, this is what it is. Um, yeah. So if you have any questions, please. We have already overshot time, so we can take the questions offline on the WhatsApp group or on the Embedded UVM forum. All right. So that's it for today.
Thank you, sir.
Yeah.
So question answers, I think so almost like after.
Okay, if you want me to take some questions, I can do that. But some of the questions are related to, are actually for
Yes,
you.
sir, they are related to the management related.
Yeah.
I think so, sir. Almost you addressed all the questions.
Yeah, actually, the session today was slightly deeper, so people will, because I know it from personal experience, the design patterns and all, though they are important, but it takes time to sink in. So I don't expect too many questions. There is one, please explain the difference between UVM sequence and virtual sequence with an example. So you can see the example in SHA3 test bench that I have shared. So basically, a sequence is created in the sense that you will be you will be creating data over there. While so it's the top every top level sequence, every top level sequence will be a sequence, and if there are sequences in between, those will be virtual sequences. So a normal sequence will not have any input, so it will generate a sequence, while a virtual sequence will take an input and modify that input to create another sequence. So that's the only difference. So don't go by the word virtual, that confuses you. So sequence which is modifying a parent sequence to create another sequence is a virtual sequence. That's it. In UVM, we write the agent and outer class code in SV or UVM, but in embedded UVM, code is written in Verilog, and then D is automatically creating, and we are not writing any UVM code ourselves, so we don't have to write actual code in this. I think you are confusing a lot of stuff. I'm not saying that in embedded UVM you don't write any code. I'm saying in embedded UVM, many of the things you write in system Verilog are automated, but still you will need to create a test bench structure and test bench functionality yourself. Only the boilerplate is reduced by way of defining attributes. For example, the build phase we could automate, but the connect phase is not automated. So it's just like as it would be in system Verilog. So that's what is the boundary of a constraint? So I don't know, like when you say boundary of a constraint, I don't know what it means. So I haven't used or come across this term, boundary of a constraint. Okay, please explain difference between this I've covered. So any question you still have, I would say we can take it up in the WhatsApp forum, or we can also take it up on the UVM forum where you can create a thread and I'll reply to that.
Yeah, sir, I think so. Right now there is no questions, and we have kept a question answer session from 6 p.m. to 9 p.m. The reason is that there are continuous questions coming up, and few participants were saying that they are not being addressed. So we are keeping a window for the question answer session so that we can revert back to all the queries. And there is a query related to the attendance, YBT Sundari. We will get back to you, already informed. So you don't have to worry, we will get back to you.
Okay,
So I
there is one question. There is one question I would like to handle, and that's about somebody is asking about why I invoke. So this is a question. While assigning data to strobe signal, 2-bit has been used. What's the purpose of using 2-bit over here? So see, in Verilog, we have this Kocha, where in Verilog, if you have smaller bit size, for example, strobe signal is only 4-bit. So we can assign it from a bigger variable, or where the bit size is larger. For example, I can assign a 4-bit variable from a 32-bit variable. So Verilog won't complain at all. So in Verilog, I can assign something like this. Strobe equal to whatever value, and that value is specified as integer. Okay, in embedded UVM, we don't want to allow that, because if you allow, you will be masking bugs, because people have written code in design in Verilog, and they would have maybe uh, done some at some places they may have assigned values from one variable to another variable, thereby losing information, especially in the reference model. So, by the way, there is one study on software which just finds out, for example, if you have a counter and you keep incrementing it, so there'll be places where it goes beyond. If the software is running for days, it may go beyond 32-bit boundary of an integer. So these are called overflow errors. Okay, so there has been a study by a university which says how many softwares have this kind of error, and that's a large percentage. Like it's more than 20% of softwares have this kind of bugs. Okay, so now we want to avoid this kind of bugs where people are at least this time. So counter getting beyond the 32-bit boundary, you'll still have it in D. But in Verilog, there is another class of errors where people are able to assign a variable of larger bit size into a smaller bit size, and the compiler will not generate any. So in embedded UVM, we don't allow it, and that's when wherever that needs to be done, people need to do it explicitly, and that's where they need to invoke functions like 2-bit. So instead of allowing people to assign a bit vector from integer, if the integer is bigger and the bit vector is smaller, instead of allowing it directly, what I allow is that people call 2-bit on the variable, and when they call 2-bit on the variable, the 2-bit function will actually evaluate the integer variable and make sure that it is small in size. Okay, it's not, it's like the upper bits are all 0, and then only it will allow you to assign it to the smaller variable. Otherwise you will have to use explicit casting, and then only you will be able to assign. So that's why 2-bit is there, because it dynamically checks the size of the variable you are trying to assign to the strobe, etc. Okay, so that's what. Another question. I don't think there are many questions today. How to come out of the Emacs window after editing? So you can say Control X, Control C to exit Emacs. So, but I would say instead of doing that, so do Control X, Control H. No, not this. Control C, Control H. I'm forgetting. So you can say Meta X, Escape X, tutorial, Emacs tutorial. So I was slightly, I'm not getting that exact key binding, but control H, control T, probably it is control H, control T. So you have the to-do list here, not the tutorial. Control H, T, yes, control H, T. When you say control HT, it brings up a tutorial in Emacs. So it will take you half an hour to go through this tutorial, but it will teach you Emacs. And it's important to learn the editor this way because what happens is when you join the industry, since you are a hardware engineer, you will have certain amount of time for your for learning, and people learn their domain, but most of the people don't spend time learning the tools. So if you don't spend any time learning the tool, your productivity will get affected. So just spend 5% of your time learning Linux and learning Emacs, and your productivity will increase multifold. So go through the tutorial. So the key binding is control H followed by not control T, just T. Okay, it will bring the tutorial and you can start it. It's an interactive tutorial, just go through it. Okay, sorry, I'm not sharing screen, but if you are able to hear, then you get it. Control HT inside Emacs will give you a tutorial. Yeah, that's it for now.
The lecture notes, the slides for yesterday and today will be shared with you.
Today
I'd
I'll
like
send.
to announce. Yeah. Yes, sir.
I'm just saying today I'll send.
Yeah. And just yesterday, we already informed all the participants. Again, we are informing. On Monday, you will be having your MCQ. So please be ready for the same. So thank you, Puneet, sir. Thank you, Ravi, sir, for connecting with us. So thank you, Puneet, sir.
Okay.
So we will be connecting again on Monday.
Thanks, Firozaji. It has been, I'm surprised that for such long sessions, we don't have any logistic issues. So I think it's very good and a way to go forward.
Thank you, sir. Thanks a lot, sir. So with this, sir, we will conclude the session today.